Good afternoon, sir.
Anupam, good afternoon.
Good afternoon, sir.
So, how are you?
Yes, sir, I'm fine. I'm fine, sir.
Okay.
Okay.
I'm seeing you.
Okay. Both the sires have joined, so we can proceed. Dr. Anish, please take over.
Respected dignitaries, good afternoon to all. I am Anish Kumar Shah, Department of Computer Science and Engineering, NIT Silchar. A brief introduction to our session chair. It is our great privilege to have with us Joint Session Chair Professor S.K. Singh, Professor in the Department of Computer Science and Engineering, IIT Varanasi, with more than 20 years of teaching experiences. His research field is bioinformatics, computer vision, image processing, video processing, pattern recognition, artificial intelligence. Sir has guided 14 numbers of PhD scholars and in ongoing total 4 PhD scholars, 4 published patents and more than 150 publications in reputed conferences, journals and book chapters, and having more than 2,400 citations. Sir has 4 number of books and 4 research projects as well. Once more, I welcome you to this session, sir. We have another eminent professor, Professor K.L. Vaishnav, sir, Associate Professor in the Department of Electronics and Communication Engineering, NIT Silchar. Sir, having more than 23 years of experiences, his research field is analog VLSI, RF design, communication engineering, analog circuit for biomedical applications, RF CMOS circuit design, etc. He has more than 90 publications in reputed journals, conferences, and books chapters. Sir has guided 6 PhD scholars and ongoing 7 PhD scholars. Sir has 3 books published and 3 sponsor projects as well. Once more, sir, I welcome you to this session. Sir, over to you.
Thank you, Anupam. Dr. Anupam.
Yes, sir. Yes, sir. Please.
Yeah, thank you, Dr. Anish also. Okay, then I think professor is there now. One more professor is there.
Yes,
Professor
sir.
S.K. Singh. S.K. Singh.
Okay, sir has joined SK.
Yes.
Okay, so right then what is the procedure for this proceeding?
Sir, we'll go for the paper number ID 012.
How much time you are giving for that?
We have given 10 minutes for presentation and 3 to 5 minutes for question and discussion.
Right. Okay, then I'll just request to Professor Shina sir, please to have some comments and so that we can start the program.
Yes.
Shina sir, over to Shina sir. Okay, sir is not connected, I believe. Okay, then I believe we may invite the first paper. Okay, the delegates for the first papers of this session. Can you invite?
Yes, paper number 12.
Yeah.
Effect of vocal loading on singing power ratio and singers format in Indian heavy metal vocalist S.V. Narasimhan and Mahesh Somia.
Right. So
Yes, sir.
welcome, please. Aishwarya, I believe so. Aishwarya. Is it Aishwarya?
No, Somia.
Shomya.
Mahesh Somia.
She has joined?
Yes, sir.
Yeah. Then please, you please, over to you, please. Okay. Shemma, SB,
Please share your presentation.
screen.
Yes, sir.
Okay. Meanwhile, one request, sir. Vishnu Yarlagada
Manish,
has
can you send the
sir.
list of the participants or the delegates in my mail so that I can see that?
Sir,
Can you share it?
already shared in the same mail.
Share. Thank you. Again, I'll check it. Okay, please.
Yes.
Yeah, thank you.
Vishnu, what was your paper ID?
Sir, it's 52, sir.
Sir, paper ID 52 has one request. So he has some meeting. So can he present after this paper ID 12?
Yeah, no issue, please. No issue.
Okay.
Shall I start, sir?
Yes, you can please start. Okay.
Good afternoon, everyone. So the topic of presentation is the effect of vocal loading on singing power ratio and singer's format in Indian heavy metal vocalist. So the introduction. Specialized voice techniques, conventionally referred to as growling or screaming, is frequently used by the singers, especially in hard rock or heavy metal music genres. These techniques are used to add a distinctive color to their voice, to enhance their expressivity and project their voices. These singers use various adjustments of vocal fold and vocal tract to yield harmonically more vibrant voices. However, most of the heavy metal vocalists tend to overuse or differently use their vocal systems for singing, and this can have an adverse effect on their quality of voice. Singer's format is a perceptual correlate of a ringing voice quality, that is a twang and resonance, which is also called as resonant voice. It is a peak in the spectral envelope around 3 kHz, but also it has been identified as a collection of the fifth, fourth, and the third format frequencies in the spectrum rather than a single extra format. Singing power ratio is one of the measures to quantify the singer's format. It is the difference between the amplitude of the most significant peak in the spectrum between 2 to 4 kHz to that between 0 to 2 kHz. SPR offers a quantifiable and its tremendous training. Moving to the need of the study and aim of the study, with the increasing popularity of the metal singing genre and a growing number of metal singers in India, there is need to investigate the singer's format and SPR in the voice of an Indian heavy metal singers. Further, there are limited studies that have documented the effect of vocal loading or vocal fatigue on the SPR or the singer's format, especially among the Indian. Objective of the present study was to document the impact of vocal loading on singing power ratio and singer's format in Indian heavy metal vocalists. The method. The study consisted of 10 male participants of the age range 25 to 32 years, and initially a questionnaire was used to assess the phonatory habits, and the phonation sample of those participants of R was recorded in two instances, that is in condition 1 and condition 2. In condition 1, it was recorded 30 minutes before the vocal performance, whereas in condition 2, it was recorded within 30 minutes after the completion of vocal performance. Data collection. The phonation samples were recorded using a unidirectional microphone placed at a distance of 10 cm from the corner of the mouth onto the Pratt software at a sampling rate of 44,000 Hz. The recording was conducted in a sound-free room. the data analysis, IM-peak software was used and harmonics peaks was identified in the spectrum envelope between 0 to 2 kilohertz and 2 to 4 kilohertz. The highest amplitude peak obtained in the region of lower harmonics and the highest amplitude peak obtained in the region of higher harmonics and peak frequency of the highest amplitude obtained in the region of higher harmonics was extracted. The power ratio of the most significant peak between the higher harmonics and the lower harmonics region was calculated and expressed in decibels as SPR. Statistics. The paired sample t-test was carried out to find the significant difference between the two conditions. Results. So this is the table which gives information on the Singer's format and SPR for condition 1 and condition 2 in heavy metal ocalist. The SPR for condition 1 were found to be higher when compared to that of condition 2. Also, the ratios obtained for both the conditions were negative. Mean Singer's formant was higher in condition 2 compared to the condition 1. Higher variability of SPR and Singer's formant in condition 2 compared to that of a condition 1. This is the figure which gives information regarding the mean and standard deviation of SPR. It is in the left one, and the right one, the Singer's format. The inferential statistics revealed that SPR in condition 1 was significantly higher compared to that of condition 2, and there was no significant difference in Singer's format between the two conditions. Discussion. SPR reduced in Indian heavy metal singers after the performance or vocal loading. Earlier investigations that have also reported higher SPR as a result of higher and a perceptual reflection of a good singing voice quality. Whereas lower energy relationship between the higher and lower harmonics resulted in lower SPR and reflected poor singing voice quality, which can be due to the varied physiological competency while singing performance, especially in the heavy metal singers. Perceptually evaluating growl-like voice in Western metal singers showed that the voice of metal singers to be predominantly harsh, whispery voice throughout the song. And these professional singers, in addition to using muscular tension adjustments, demonstrate the higher levels of laryngeal tension. The additional force which is produced by the exhaled screams is discerned to be particularly exhausting on the performer and more destructive than the inhaled screams. Considering all these adverse effects of the vocal behavior of metal singers, the spectral measures such as SPR are bound to get affected. Although there was no significant difference noted in the singer's format between the pre- and post-fatiguing conditions, higher format energy was observed in post-fatigue condition compared to the pre-fatigue condition. The present study also evidenced the singer's format ranging from 3 to 4 kilohertz, and these findings are consistent with the previous results reporting center frequency of the singer's format ranging from 2.2 to 3.8 kilohertz. Thus, it can be inferred that the power of the most significant harmonic peaks in the frequency range between 3 and 4 kilohertz is vital for singing voice quality among the Indian heavy metal singers. To conclude, the results of the current study showed higher SPR for the pre-fatigue condition compared to the post-fatigue condition and no significant change in the singer's format frequency in both the conditions. Thus, SPR can be considered as a quantitative measurement for the estimating singing voice quality as it provides a distinctive correlation with the effect of vocal loading on the Indian metal singers. Further studies can throw light on calculating these spectral measures in heavy metal singers during their vocal performance as the singing style involves specialized screaming techniques such as growls, grunts, squeals, and distortion in comparison with the non-singers. These are my references. Thank you.
Yeah, hello. Shri, actually, what exactly you're trying to do? Not hello. Okay. I'll ask question from the audience, please. Okay. Any question from the audience? Then I'll look back to the audience. Any question from audience?
One question, please.
Yeah.
See, a human hearing range is from 20 to 20,000 kilohertz. But while singing, we go for more than that. So why do we go for this more range? Ashira, please unmute and answer. We can't hear you.
Sorry, sir. Can you please repeat the question, sir?
The question is that human hearing range is from 20 to 20,000 kilohertz. I mean 20,000 hertz. But still, singer, you are saying that they sing up to range around 44,000 hertz. So why so? Why we?
I couldn't hear you, sir. Can you please repeat it again?
My question is that human hearing range is from 20 to 20,000 hertz. Okay. But while recording or while singing, singer used to go above this range. For example, up to 44,000 hertz. So our audience.
We kept the sampling frequency as. Yes, sir. So we kept the sampling frequency as 44,000 hertz, so as to have a better representation of the sample. That is, more the sampling frequency, better is the storage and better the analysis.
Okay.
Yeah, any question from any others delegates, please? Any more question? Okay. Then Oshirya, I have one more question. Okay. Can you?
Yes, sir.
Yeah. Can you show your slide again? Can you come to slide mode again?
Yes, sir.
Yeah. Yeah. Fine. As you said that one of our respectable participant as well as the delegates said that regarding in terms of sampling frequency, you said higher sampling frequency, it will store a lot of data. That's fine. But you know that what extent you have, what extent sampling frequency you are looking into that. It is in general, okay. As you said, higher sampling frequency will what? Will give you more storage or what? More informations, so that you can have better information. Do you have any sort of redundancy factors?
So basically, our
If
speech.
you have a more higher sampling, more redundancy, you need more processing time, obviously. So that point also had you thought of?
Yes, sir. But our the speech lies within 20 kilohertz. So anything more than double of that will be ideal for the sampling frequency.
Okay, fine. So, fine. Thank you for your answer. But what is your target? From this work? What is your target? Hello.
So by this, yes, sir. So by this, we
Elaborate
can.
your target exactly. What is your elaborate your target? Can you elaborate a little bit?
Yes, sir. So by this, yes, sir. Am I audible, sir?
Yeah, audible. Very much audible, please.
Yes, sir. So by this, we can start educating the individuals that we have to follow certain vocal hygiene tips or certain modifications in their singing techniques, or we can create awareness in them, sir.
Okay. What sort of awareness you are looking from there? What sort of awareness you are looking to that? Technical points. Can you bring your first page?
First,
Madam, can you bring your first page?
sorry,
Yeah.
sir.
Effect of vocal
First.
loading on, just a minute. Effect of vocal loading on, just a minute, first page. Effect of vocal loading on singing power ratio. Okay, and signal and singer format. Indian heavy metal vocalist. Okay. Can you talk on that, some preview on that? Can you give me some preview on that? Hello?
Yes,
Ushuria?
sir.
Yeah. Can you give some preview? Why do you need all sort of things? Vocal loading.
Yes, sir. So basically, usually we see that the classical singers or heavy metal singers, these singers who are untrained, or they may use a false technique, or they might not follow the vocal hygiene tips, as in taking enough water, or a few still practice the smoking, or still have a habit of smoking or alcohol intake. And in this generation, there is the Indian heavy metal vocalist this thing is more growing, and the number of individuals who is practicing this also is increasing. So because of that, there is an awareness that has to be created.
Okay. Thank you. Thank you, madam. I think you are Ushuria, na? Is it what? Am I wrong?
Yes, sir.
Or you are Shammo?
Yes, sir.
Okay. Any other questions, please? No, I think no question from other audience. I'll over to our one of the chairs is our Sheena sir. Can I over to Sheena sir? Onish, Dr. Onish.
Yes, sir.
Sheena sir is on the line or what?
Yes. May I request Sinha sir to give some suggestion? Hello. Hello, Sinha sir. Singh sir.
Okay. Fine. Then if there is no question from audience, Onish, I
Yes.
hope so. Maybe some technical problem with Sheena sir.
Yes, sir.
Then we'll give a thanks to Shammo and that's Ashuri for presenting the things. Audience, I'm thankful to the one audience really, and this participant and or delegates, whatever, really put the observations, and Ashuri has given the really replied correctly. And with this, we must thankful to the Ushuria for joining the sessions, for forwarding his valuable work to this conference. Thank you, Ushuria. Thank you.
Thank you, sir.
Okay, we move on to the next paper. Paper ID 52, Music Genre, Classification and Convolutional Neural Networks and Comparison with FQ and MEL Spectrogram Based Images. Writer Aditya Dhel, Srinivasa Murthy, YB, and Shahidar G. Kolagudi. Paper ID 52. Okay, could you please share the screen?
Hello, yes, sir. Am I audible?
Yeah,
Yes.
you are very much audible. Huh?
Is the presentation, can you see the presentation?
Yeah, you can proceed, please. Huh?
Yeah. Okay. Yeah. Good morning, everybody. I thank you for allowing me to present my paper in the 25th International Conference on Frontier of Research in Speech and Music. So my paper's title is Music Genre Classification with Convolutional Neural Networks and Comparison with F, Q, and MEL spectrogram-based images. This paper is written by Aditya Dhal, which is me, my professor Srinivasa Murthy, and his professor Shashidhar Kolagudi, who is in NIT Silchar. So this is a brief overview of what we are going to discuss, which is the information which can be retrieved from the audio signals, other related work, our proposed methodology, the database we chose to work on, the whole process of spectrogram generation and the result, and what we plan to do in the future. So first, I would like to highlight some basic features that which can be extracted from a sound wave, such as the the singer's gender and singer and instruments and the repeated patterns, then emotional patterns or album instruments, etc. So yeah, over here, so let's say for example, if we take genre, so genre is helpful to classify the music into music, which makes it possible to decide the song category, such as rock, pop, hip hop, and so on. And yeah, you can use like many of these features have been used in the past, like are being used to classify the genre. So yeah, again, music song similarity, all these are being currently used, but due to a certain lack of metadata, that is due to a certain lack of meta information for most of the tracks, it is not a very feasible option. So yeah, so what we need to provide an efficient automation tool to effectively classify the music genre. So what we have yeah, so and then yeah, so some of the features that we have used, like which have been used in the past, are MFCC spectral features, and in the KNN method, or constant Q transform in the linear magnitude and log magnitude method, and so on. But the feature we are focusing on is spectrograms in CNNs. So since like due to the recent development in the CNN models, we are being like we are able to classify images properly, like more effectively into respective categories. So this is a general flow of our project project. So we selected a data set, which in this case is the GTZAN data set. So out of that, we extracted 3 different types of spectrogram images: the F transform spectrogram, Q transform, and MEL transform. Now all these these 3 different types of spectrograms are resized to 244 and 32 by 242 244 by 244 224 by 224 and 32 by 32 images respectively. And this is done because after a lot of research, we noticed that most of the people who are using the CNN models like AlexNet and LINET 5 are using 224 by 224 and 32 by 32 images respectively. So yeah, in our case, we have used the GTZAN dataset. So in this dataset, there are a total of 10 genres, and each genre has 100 clips of 30 seconds long each. And the genres include blues, classical, country, disco, hip hop, jazz, metal, pop, reggae, and rock. So for training purposes, we used 70% of the data for training and the remaining 30% for testing. So yeah, and all the recordings are at 44.1 kilohertz of sampling frequency. So yeah, these are FQ, and these are like images of F transform, Q transform, and MEL transform of one audio of 1 30-second long audio file, respectively. Yeah. So we have passed this data to AlexNet and LINET 5 CNN models to test their accuracy. And so the reason we chose AlexNet is because in 2014, in the ImageNet competition, it won won very dominantly. But again, so it is very difficult to implement. But we needed it is very difficult to actually implement in the practical capacity. So, but its advantage is, but we needed a arbitrary environment to efficiently test our sample cases. And the other CNN model we have used is the NET 5, which is in fact a very old model, but it has been like it's very old model. It was implemented around 1998, but due to the lack of efficient hardware, it never gained recognition. But now even a generic CPU can execute that code. So this table, it represents the data that we have extracted after training each CNN model with the respective spectrogram. And so what the problem is that Q transform and the spectrograms have too much the music signal is highly complex in nature, so the image is still not up to par. So yeah, these are the accuracies and test accuracy that we derived after training. And the following are F transform, Q transform, and MEL transform graphs achieved in AlexNet, and then LeNet in normal gray normalized form, and then LeNet 5 in just grayscale form. So after looking at the following data, we can easily conclude that Q transform and MEL transform easily surpass F transform spectrogram images in performance and in accuracy. So, Q transform in this scenario slightly, marginally performs better than MEL transform, and so since moreover RNNs are also are suitable as they are capable of extracting the features directly from the raw signal, and in our future work we will try to in our future work we throw light on the aspect to compare the accuracies of various available data sets using CNNs and RNNs. These are some of the references we've used. Thank you.
Yeah, thank you, Aditya Dal, Srinivas Astava Murthy, and I think Shashidhar. Thank you all three.
Shashidhar G. Kolagudi, sir.
Shashidhar
G. Kolagudi.
Yeah, very difficult name. Sorry for that. Thank you all three really for presenting, and the work is very promising work, because you are using machine learning and then music industry. Really a great job you are doing. So first of all, I'll move to this our participants and other delegates. My colleagues, friends are sitting over there. Maybe a few of our students also, PhD students also sitting. Any question from this from that side? Okay, please. Any questions? Welcome. Question from for the audience, please. Any question? Question? No question.
Yeah,
no question.
Question,
Doctor, please, Dr. Shah. Dolunde Singh. Okay. Yes, Dolunde Singh. Doctor, please.
Can you please explain what is spectrogram?
Yeah. Aditya, please response to the Dr. Dolinda Singh. Dolinda, your voice is not clear. Hello.
Okay. Can you hear me, sir?
You are in the campus or outside?
Campus, sir.
Yeah, campus. Okay. Yeah, please. I think Aditya is there to raise the question.
Yes, sir. Yes, sir. It's a spectrogram is like a visual representation of the frequencies in a sound in a wave of sound as it varies with time. So that is what it represents. It's yes, sir.
So in your slide, it means according to the genre, this spectrogram is going to be different.
Yes, so they show some difference. Like even visually, if you look at them, even in F transform, Q transform individually, they show some visual differences. But in some cases, in some genres, the images actually are quite similar from from a human visual thing, a point of view. So which is why our objective is to pass them in CNN models so that they can go into detail and uh, nitpick on the details and differentiate.
Okay.
Yeah. Thank you, Aditya, for giving a response to our professor. Then any other questions from the audience, please? We are thankful to Dr. Dolindo for putting questions every time. Very good. It's really making active sessions. Okay. We expect more questions from the audience.
May I request Singh sir to give some views about the paper ID 52?
Yeah. Any other question from audience, please? Okay. If no questions, a question from me. A few more down to me. Aditya, are you online?
Yes, sir. Yes, sir.
Aditya, yeah. Aditya, can you give a little bit more light on that audience, because audience may be from different background. What do you mean by music, the genre that you want to say?
Yes, sir. So, sir, each song belongs to a certain genre. So, genres are created so that similar types of music can be classified appropriately, and so that music apps such as Spotify and Ghana, and they can make efficient
Now that I
recommendations.
understood that in terms of genre you can classify. Can you put more light on what do you mean by genre?
Culture.
Yeah.
So yes, so genre okay, to go a little more technical, sir. You can classify waves with so songs with a general similar wave pattern or sound
Tell
wave
in
pattern.
terms of Aditya, please tell in terms of technical term. Okay, not a generic term. Okay. In terms of frequency, in terms of, because you have the moment music is there, frequency is the big issues come. Okay. So why not you classify? How do you classify your generic? As you said that we can classify the music into different types of genre. So what are the features? What are the attributes to classify the music genres?
smoothness in the instruments, like high pitch, high loudness,
Right,
and
Vishnu.
low pitch, low loudness can be categorized into based on those parameters we can categorize.
Yeah, right. You have a set of the attributes, okay? Then you will put into a particular class, is it not?
Yes, sir.
Yeah,
Yes, sir.
yeah, right. So my next second question, you use convolutional neural network. There are so many that neural networks are there. Why do you thought of convolutional neural network?
Sir,
Since it is recently it is popular on the images, so and moreover since we wanted to convert that till now the tasks on gender classification is mostly done on the handcrafted features, sir, like we have extracted by using the signal analysis. So initially we recently had done one music mode estimation task, so using spectrograms I found little improvement in the performance, so hence I wanted to do the same thing with my student in terms of general classification. So later we will try using that direct signal feeding into RNN, as well as using the different data sets. There are 13 different types of data sets on genre. So we wanted to extend this work also. So we have submitted a little work for this conference.
Yeah. Okay, thank you that you also joined, because you are the supervisor, I believe. Aditya is your scholar. Very thankful to the entire group you have joined. We are delighted from NIT Silchar, the entire group has joined Place to Work, and we appreciate the way you are working. We look forward to have more collaboration with the NIT Silchar also. Okay. And thank you all. Aditya, the Bal, then I think Dal, then Slibash, then I think Shashidhar, Dr. Shashidhar, I believe so. Is it not? Huh?
Yes, sir.
Yeah, very good. Thankful to that. You also join along with the team. I'm very thankful. Okay. So
Thank you so much, sir.
For the audience, I hope we must give a thanks to entire group for really sharing their valuable research work to NIT Silchar and their conference. Okay. It will add on really glamour to the entire platforms. There are many participants, many delegates. I hope so that they'll be inspired to work on those areas. Okay. So with this,
and we are very thankful to the organizers of FRSM, sir. So we are delighted to present the same in FRSM.
Thank you, Dr. Vishnu. Okay.
Yes, thank you, sir.
Group. Okay. So with this, I believe we'll move to the next one. Okay. Now I'll over to Dr. Onish to invite the next participant.
So move on to the next paper ID 17.
Dr. Manish.
Sir, please, sir.
So, am I audible? Actually, my voice is not coming to you, you people.
Sir, please, sir. It is audible, sir.
You are audible. So, is it audible to others also? I think.
Yes,
sir. It's audible now, sir.
Okay, so
yeah, Shinasa, now it is audible. We are actually looking for you. We thought of some technical problem.
Yeah,
sir, you are again welcome to really these sessions.
No, Thank you,
we
sir.
are missing you, sir. Okay.
So actually, I wanted to ask one question, but I think I was not audible to you people.
Yeah, we did not listen your question. Right. Maybe some technical problem. Okay.
Okay.
Now it is fantastic. Everything is audible, sir.
Okay. Now, yeah. So it's okay now. So please go ahead.
So, Dr. Onish, please invite the next one. Okay.
Okay. Move on to the next paper ID 17. Classifying hate speeches shared in Twitter. Writer Dipankar Das, Shobhik Mandal, and Antarikya Roy.
Hi everyone. Am I audible?
Yes. Could you share the screen?
Yeah, sure. Hi everyone, good morning, good afternoon. I am Sovik and I will be presenting the paper on classification of hate speeches in Twitter along with Antarikya Roy. So primarily social media has grown a lot in the last couple of years, particularly starting from as a MySpace in 2005. Now, as a statistics, around 6,000 tweets are generated every second. So what we wanted to do was we wanted to analyze the tweets that are being generated and to classify them into various categories. Primarily, we focused on hate speech detection because that's like a difficult and as well as a challenging task. Now, initially, like we wanted to build a full system that will analyze each of the tweet and it will classify it into further categories, but it was very time consuming to process each of the tweets. So we wanted to develop a low latency and high throughput system. So for example, if we have like 6,000 tweets in a single second, so we wanted to process them as faster as possible. So we wanted to make the classifier to remove as much as false negative we wanted, and also to filter out the false positive. So particularly first as a description, what we have used as a hate speech. Hate speech is any type of speech which attacks a person, group on the basis of race or gender or sexual inequality. Now to develop this system, first our initial approach was to have a low latency system. For low latency system, we didn't want it to process it to further multiple classifications or multiple layer CNN. So we went with one single CNN layer, which will be a much faster. And if you say, for example, it will be able to classify the tweets in a real time. So if passing a tweet wanted to bring down the processing time to under 300 milliseconds, so that we can process much faster. So basically, we started with 4 different models to classify that tweet. So initially, it's like we started with the normal unique words. So what we did here is like we took out each of the tweets. We removed all the irrelevant details. Like for example, you were mentioning someone, or you were there's a name or a place in there. We wanted to remove those which are not actually relevant for classifying whether it's a hate speech or not. So that's the pre-processing part we did. Now it would be faster because we are not doing much of a parse tree. So we generate a simple analytical parse tree and we check, okay, this is a noun and this is a name. So we ignore those details for now. We'll be adding those details later for further improving the categorization. But for now, we just initially remove those categories. We actually just put it in a simple feature vector. So initially our feature vector was pretty high because if you consider all the unique words, it will go very, very high. So we found that the accuracy was dropping a lot. It was around 60% or so. So that's not a good way to do it. So then we started using the n-gram model. So why 4-gram model basically? We started with 3 gram and it went to 6 gram. So we noticed that 4 gram, like at 4 gram, we have a high success rate, and also after 4 gram, the success rate or the accuracy doesn't increase much, but the performance drops a lot. So generating something into 5 gram, generating 5 grams of each of the words will be very costly. So we went with 4-gram model, a 4-gram model and TF-IDF. So initially, as I said, like we removed some of the normal irrelevant details earlier in the pre-processing using the analytical parsing. But in here, we actually went and did the TF-IDF. Initially, pre-calculated TF-IDF. So in our data set, to call that tweets, we calculate the TF-IDF score of all the words that we had, and then we applied only that TF-IDF score. So for calculating TF-IDF, we haven't used the normal words that you find in any normal paragraph or text, because Twitter tweets tends to be a little short. The words are not complete. So for example, you can represent DN as THN because there is a word name. So people tend to use shorter words. So we cannot use the TF-IDF score of the other words that are available in paragraph. So we only went with the TF-IDF score of the tweets. So that's the second model, TF-IDF score, and 4 terms. Now, it generated a feature length of not very high, but when we actually passed through the CNN and we took the output and we ran it on our test data, we found that okay, the accuracy is around 76%. But what was happening is like some tweets doesn't have a negative or we're not considering the sentiment score of the tweets. As such, we tried introducing the sentiment feature. So sentiment feature is simple. It just produces a vector with a positive negative score. That is used by, we use the CNT1 to do the classification. So that will give you a positive negative score, and we'll add some weight to that, different from what we're actually giving to the weight of the other input layers. And we found that if we add the sentiment features, then we are able to classify the neutral speeches much better. So the accuracy went up by 5% for the neutral speeches. So we're basically eliminating the false positive and the false negatives when you're using the sentiment model. So we went to TF-IDF plus foreground plus sentiment model as our feature vector. Now, adding the sentiment model does increase the time complexity. Initially, the complexity was like each of the tweets are getting processed under 300 milliseconds, but after that, it's taking a little longer with 330 milliseconds. But we went with that approach because it actually reduces the number of false negatives. So currently, if you look into tweets, how the tweets get processed is like manual workflow. So, for example, if get a tweet or maybe you get a post in Facebook, you see, okay, this is a hate speech, so you just go and report it. Now, that reporting actually goes to a manual person who just takes about a second to determine whether it's a hate speech or not. Now, that process is not effective. So, we went actually this approach. This will be able to process tweets much faster, and also it can actually correctly classify whether it's a neutral or not. So in our primary aim was to have a very high accuracy for the neutral speeches, but we can compromise with the little offensive and hate speech determination because we want to minimize the number of manual touch points that are in the flow that we want. So we source the data from Cloudflower. So that's like 12,000 tweets that we had as our data set. And we out of that we divided into various different partitions, some with equal to some with unequal number of hate speeches and neutral speeches, and then we use that to train the model. So for example, initially we divide the 12K tweets into two parts, say 6K tweets for testing only and 6K tweets for training, and within that 6K tweets we further divide into various data sets we wanted to check. So if we want to move, say for example, from one language to another, for example, we wanted to move from English to some other language that uses the same alphanumeric set as English, we wanted to check out what is the difference or what would be the change in the accuracy or the training features if we do that. So initially we just went with English data sets, so 6K data sets for testing and 6K for training the data set. So initially we took 2K tweets of each, like the hate speech 2K tweets, offensive 2K tweets, and neutral 2K tweets. So that's using that we actually trained the data, and we found that we have by using the above CNN network. Now for the CNN network, we used a simple sigmoid function because we don't want to increase the time complexity on that. Now it's a 2K tweets each, and we processed it, and we found that in the case of around 93% of the tweets are correctly getting classified as neutral. Initially, as I mentioned earlier, we have a 5% increase over after adding the sentiment score. We have a 90% increase of the tweets, so that's pretty high level of positive cases that we're finding. So we remove those things from the result. Now, for the hate speech and the offensive speech, we found that if we say if we train with equal sets, so 2K tweets each, we found okay the accuracy is around 83%. But if we actually have the training data set with unequal number of tweets, so for example, say what 2K tweets for hate and neutral, but offensive we used in 1K tweets, we found that it's getting biased and the accuracy is going down. So for training only, for training purposes, we use equal number of tweets from each of the data sets. We found that the accuracy is increasing if we use equal, and if we accuracy is lower if we use unequal data set. The accuracy for offensive speech is around 83%, and for hate speech it's coming around 76%. Now, for the future work, we are trying to use some other models except the CNN, but we are aware of the time complexity that will come in picture with that, because we want to process a high number of tweets, so we want to have a high throughput. So we have to be careful on the model that we're using. So for future work, where we're trying out some different models, we can try RNN, but it's still in work in progress. And we can also try to do with some other language that uses the same alphanumeric character set as English. So the challenge over here is like we cannot change it for a different language. except English that uses the English characters. Because we're using a N-gram model sets, so it will be difficult to classify, like divide the corresponding one into different N-grams. So that is a challenging for the other languages.
Yes.
And I'd like to
Shobik,
mention,
is it over? Yeah. Thank you, Shobik. Shobik Mondal and entire group, really. Before putting any questions, I'll move to our Professor Shina sir. I think online. Shina sir? Yeah. Sir is now okay online. We'll listen from the suggestion from Professor. Okay. Sir, any short of observation? Hello. Shina sir? Shina sir? Maybe sir is trying to say something. Maybe some technical problem. Onish?
Yes, sir.
Onish,
Yes,
is
sir.
it audible to what sir is saying?
No, sir. I think there is some issue
Maybe
of.
some technical problem. Okay. We'll come to sir again. Then we'll go to that students, okay, and participants, delegates, other faculty members also there. Yeah. Any question from this audience, please? Okay. No question. Very good. I think yeah. No. Hello. Yeah.
yes, sir.
Any question from audience? No. Then Shobik. Yes.
Yes.
Can you come to your first slide? Shobik.
Sure.
Yeah. Can you come to your first slide? First slide. Name of the thesis. Name of the your that work. Yeah. Classifying hate speech. Very good, because this is really hot topics for nowadays. Very good. Your I think along with you there are other members. Okay. Your Professor Dipankar Das. Then others. I think A. Roy also there from Jadavpur University. Enter group is Jadavpur University. Very good. Your
you, sir.
participations really. And what my question that how do you classify? What are the features that you take to classify this hate and other sweet speeches?
So for classifying the features,
Yeah.
for classifying the features, we use the N-gram model. So N-gram model is very popular. Elasticsearch uses it for their internal classification and searching purposes. So N-gram model is easy to implement also,
No.
and it is not.
Shobik, my question is not to this point. My saying that what are the attributes basically? I'm a layman say. There are many people from this may not be this area, but they may be motivated. They may be encouraged to work on your area. Okay. To motivate them, my question. To motivate many of the audience, you tell me that technically what are the attributes that you consider? Sorry.
So if you consider so if we consider a tweet is basically a collection of words that we have. So, but that collection of words does have a context. So the first way to resolve the context, you can group the words. Okay, this word is referring to this person and etc. Now, if we want to make it faster, so the initial option is just you can just find the offensive word in there and say, okay, there is an offensive word or a curse word in there, and that is offensive. But that is always not correct. Because Twitter tends to be short. You only have 60 words to actually give that. So people tend to write shorter words. So what we did was for extracting the features, we took that. Say for example, it has 20 words. We have 20 a feature of 20 words each. So say for example, my tweet was hello, hi, how are you? So I have hello, how are you, and 4 words, 4 features. But further we distinguish it into multiple n-grams models. So for example, if hello is the word and we are doing n-gram, then 3 grams, say we do HELL, LLO, and like that. So that way, for the feature vector, we have the words that we are giving, and the words in the correct order. So, for example, we don't want to attach the word that is in the beginning to the word that is the end. That is a further work that we can try to match the context. But for these purposes, we have not done that. What we have done is like check the words in sequence. Don't break the sequence. Then remove the irrelevant words. Like say, for example, hello, how are you? So R is not relevant in most of the scenarios. So we're left with hello, how, and you. So from there, we have 3 words. So that replaces our feature vector name. The whole purpose was to minimize the time taken to parse each of the tweets. So we could have increased R, but that would have taken the feature vector in much faster and would take more time. So we will basically reduce it to hello, how, and then we proceed. Similarly, there are some offensive words, for example, that people tend to write. Is like they will not write the complete sentence. They will add say some asterisks, some at the rate, those things. Those things, for example, if you want to mention someone's like, for example, nigger, you say N-I ***. So, for example, that is actually blocking the view that it doesn't have offensive word, but it's actually offensive. So what we did was like we can have N1 star as in-gram feature. So we know, okay, this is probably pointing to something negative. So that's why we do the classification.
Yeah, Shobik, thank you to for giving the detail, really the explanations. I hope so that many of the audience will be motivated to work on this video. And work is really huge volume of work. There's a lot of potentials for this work. Many, I think, industry is really looking for this sort of work. Because yeah, Shobik, one more question. If I add on that. You have used, I think, neural network, hidden layer, many things. How many hidden layers you tried for that?
So initially we tried with only 3 layers. Then we showed, okay, then if we use 3 layers, the time complexity 100 milliseconds. So we came down to only 1 hidden layer because that is enough. That is giving enough accuracy. If we can add multiple hidden layers, we can add another hidden layer, then 2 hidden layers. But that is actually increasing the time complexity for the CNN model. So if we find some other neural network model, then it would be much better classification. But for now, we wanted to keep it under 300 milliseconds because the number of tweets, the number of posts is pretty high. So if we add another hidden layer, the time complexity is going to increase, the throughput will decrease. So we didn't want it to decrease the throughput. We wanted to keep the throughput high. So that's why we used only 1 hidden layer, but we can use another hidden layer with a different sigmoid, anything except a sigmoid function. That will work, but that will just increase the time complexity.
Thank you, Shobik. Okay. Then I think our Shina sir is still online, I believe. Shina sir? Shina sir? I think we are unable to connect, sir. Okay. So anyway, if there is no question from the audience, then we must give a thankful to the entire team for wonderful presentations. And yes, Onish, then yeah. So we entire team of NIT Silchar, really, we give a thanks to this entire team of this Shobik and others for participating and sharing their valuable work to us. Hope so that other members, other participants will be motivated to work on this. Thank you, Shobik and entire team. Thank you. Now over to Onish.
Thank you, sir.
You can invite the next participants.
Okay, move on to next paper ID 18, state of the art and review on analysis methods, software and application of fMRI for classification of Alzheimer diseases. Writer Chitran Barnagar and Hitesh Shah.
Hello. I hope I am audible and my screen is visible as well, right?
Yes.
No, your screen is not still visible. You can give F5. I hope so that you can try with F5, please.
Is it visible now, sir?
Not visible. The screen is visible.
Hello, is it visible?
It's not, yes.
Yeah. You now just give F5, full screen.
Okay, fine.
Thank you. You can start now.
Okay, good afternoon, one and all present here, and good afternoon to the session chair, Dr. S.K. Singh sir, and Professor from NIT Silchar, Bill Smith sir. Today I am going to present my literature review paper. It is basically a review paper, which consists of the analysis methods that is used. Sorry. Okay, so I will be presenting with respect to the analysis methods that are used, the softwares that are available in the open source domain, and application of fMRI. What are of fMRI to classify the Alzheimer's disease patients? So it is in the domain of biomedical image analysis. It is not in the domain of signal processing or speech processing. Right. So I am Chintan Varnagar, currently pursuing PhD under the supervision of Dr. Hitesh B. Shah sir. I am from Rajkot, Gujarat, India. Let's start with the next one. Okay, so I would like to throw some very introductory remarks on what is a neurodegenerative disorders. Alzheimer's disease is one of a neurodegenerative disorder. Neurodegenerative disorder is an umbrella term which is covered or which is consisting of so many different diseases, right? So in the case of each and every neurodegenerative disease, it is loss of structure and or function of neurons. Your neurons or the structure of the neurons gradually lose its functioning capability and ultimately leading to the death of the neurons, right? So if you think of this disease biologically, or if you think in the terms of pathology, at the root level, there is an accumulation of abnormal proteins in the terms of plaques and tangles. There are beta amyloid proteins, right? And out of the research and out of the literature review, it is also said that the area hippocampus in the brain is affected mostly, right, in this Alzheimer's disease, right? So the pathology begins in the one area of the brain. It means it is localized in the nature. We will have subtle or small differences in a very specific small part of the brain, right? And gradually it spreads out as the disease progresses. It spreads out across different three-dimensional boundaries across this seed point, or we can say the regions, and lies, right. So the problem, the actual problem lies in detecting those changes using different MR imaging techniques. It means the modalities. So MR machine, that is magnetic resonance imaging, MRI image. This MRI machine is capable to generate various or different types of different types of quantitative analysis methods are there. For example, structural MRI, you give structural differentiation with respect to the patients and others. We have an fMRI, that is the functional MRI. We have a diffusion weighted imaging, that is DWI, and we have FDG, PET, MRS, so many others. So these all are the different type of scans, right, that we can get from the same patient, right, same subject, same patient. We have so many modalities available with us, right? Okay. So what is a functional MRI? I am focusing this discussion with respect to the functional MRI only. Actually, in the case of functional MRI, you are trying to assess the brain activity that is present inside the brain while performing or not performing any kind of action, right? It means the person is at the rest, or the person is doing some instructed activity, for example, tapping a finger, right, doing some coordinated task. So this is what under action, right? So what we are trying to measure here is while you perform certain kind of activity, even though I am speaking right now, certain region of the brains are activated, right? So it requires more intake of glucose, right? So we measure what? Bold signal, that is blood oxygen level dependent signal. It is a biomarker, right? We have regional brain activity while performing certain kind of actions, right? Or if we are at the rest, then also certain regions of the brains are activated. They are consuming the metabolism respect things are okay, right? So the tight coupling is observed between the activity related brain metabolism and regional blood oxygenation flow, right? So there is a tight coupling. So a healthy person will have another kind of characteristics with respect to this activity and the intake of the Bolt signal. I mean the amount of the Bolt signal returned, right? And those who are having a disease will have an altered coupling. See, this coupling is altered in any other way, right? So this alteration indicates that there is an issue with respect to the person's brain, and the person is having a probability that he is a diseased person, right? So that is the main idea out of this functional MRI. Okay. Now we are having certain analysis methods. There are lots of analysis methods are there, right? Each one is able to perform a specific task, right? So I have reviewed the methods here, right? So on the left side you will have methods. These are the methods. For example, amplitude low frequency fluctuations, regional homogeneity analysis, functional connectivity density analysis, seed based functional analysis. I have analyzed with respect to the approach or working, like what is the mechanism, what is the basic fundamental behind this is working, right? It is used to measure what, right? And the advantage and limitation of this approach, right? So depending on the thing that you want to analyze, depending on the thing that you want to predict or identify, there are plenty of methods available, right? I have listed out those. It would be not possible to discuss each and every one in the short amount of time, so I'm keeping it for now. So this is what the analysis methods, right? You have to decide which analysis method is best applicable, best suitable, and what type of features you are trying to extract from the MRI scan available, right? So these are the analysis methods, right? So I've reviewed them. The next is data processing software, right? In order to process the fMRI data, there are so many open source and commercial licensed softwares are available. I have reviewed them with respect to various aspects, right? Like the aspects that I have listed here, computing environment or in which language those softwares are developed, right? Source code and programming language, capability for pre-processing of data, right? If I can only perform some kind of classification task, but I don't have a facility to pre-process those data to remove artifacts and noise and other elements from the data, it is not generally a good choice of software, right? How intuitive the UI is, graphical user interface, right? When the first version was available, right? So as long as the software is old, it is maintained and it is having a regular update. So this kind of analysis is done. How easy the documentation, installation guide, tutorials, user guides are available, right? I reviewed with respect to them, and support for other MRI imaging modalities. With respect to fMRI, that is okay. But does it have facility to perform diffusion weighted imaging data? Does it have an ability to perform any other modality that I'm interested in, right? So these are the comparison with respect to softwares, tools that we use, right? Okay. Now I'm talking about the application of fMRI to study, to classify the Alzheimer's disease patient. So these are basically the applications of AI and machine learning tools and techniques. That is, they are using different tools and techniques, right? So I will list out some of them, right? Most of the studies uses Alzheimer's disease neuroimaging initiative data. It is a large data set available in the UCLA, University of Southern California, USA. They host approximately 2,000 plus subject scans scattered across periodically, right? So I have reviewed those studies that what was the objective or purpose of those studies, right? Then which kind of data set they have used, right? Which data set they have used, what is the sample, how many subjects have been taken into the consideration, right? Whether it is a longitudinal study, it means does the study include changes with respect to the same people monitoring the progress of the disease, yes or no, longitudinal study, right? Then stages considered. Some study consider only two classes. There are three classes. The first one is an AD, that is the patient which is having an Alzheimer's disease. The second class is an MCI, that is mild cognitive impairment. This MCI is a group of people. They have started to demonstrate some of the symptoms, right? They have started to have some kind of symptoms, but they are not totally diseased one. They have just started, right? And there are certain people like you and us who are completely normal, right? Okay, so there are three basically class, right? Normal control, mild cognitive impairment, and Alzheimer's disease, right? So the study, this particular study referred out by this paper number 12, right, is classifying between mild cognitive impairment and Alzheimer's disease patient only, right? And does it conclude or include any other parameters other than this fMRI? Yes or no? If yes, which parameters are considered for? I mean, they are considered for the study, and so many other aspects has been evaluated. Right. The next one is method or approach or technique and the biomarkers used. Right. Which biomarkers they have used, that I have referred. Right. Along with this, only fMRI, does it use any other biomarkers? Right. The result and accuracy that they have reported is mentioned. Right. Whether it is a two-state classifier or a three-state, but as I already told, it is a two-state differentiation between two class. Right. And the software that they have used, statistical parametric mapping, SPM, right? So the next few slides are with respect to the same objective, right? They have used different techniques, right? In the case of fMRI only, right? Some are using 3 class, right? Some are using 2 class, and the accuracies they have reported. So these are the findings with respect to different fMRI studies that has been done, right? Okay. Now, based on this, what is my approach? What is the conclusion or the proposed model out of this discussion? Right? Look, each different MRI modalities is giving you a different perspective to look at the same patient. Right? For example, this diffusion tensor imaging. Right? This modality DTI gives you how your tissues are integrated. Right? It means it is measuring the strength and ability to function within the given context, right? And to measure this, I'm using 2 different biomarkers, that is fractional anisotropy and mean diffusivity from the DTI scan, right? The next modality that I have used is functional MRI that I have talked about in detail. Right? And the biomarker that I'm using is a bold response, right? The bold, right? Derived from this fMRI. And the third modality that I'm using is FDG-PET. That is basically a radioactive material, radionucleotide, fluorodeoxyglucose, positron emission tomography. It is giving you a biomarker as a glucose hypometabolism. So it gives you a metabolism related information, and this fMRI will give you a brain activity. Right. So now we will have so many different modalities. Different modalities will give you different biomarkers, and data from all these modalities is assigned to this classifier to train and to predict, right? The next available class, right? So that is the overall main idea out of this entire discussion, right? So that's it from my side. If you have any question, I would like to hear it, and I request a session comment and feedback and guidance as well from them. Hello.
Hi. Can I ask a question?
Yes, sir.
Yeah. Your last slide said that talks about the title is proposed model for AD classification.
Right.
Do you plan to use any of these models using any hospitals or something?
Sir, I have visited two of the medical facility centers in Rajkot as well as in the Anand, where my supervisor is working with. So we are in the close contact with the radiologists, because ultimately whatever the results we are going to produce need to be validated with the doctors, right? Because they are the domain experts, right? So we are supposed to provide an input, or you can say as an computer-aided detection system. We are not supposed to replace. We are not saying that we can replace these doctors, right? We are supposed to augment them. So that is the main idea. If some clinician is missing some details, right, we can show them that this is the chance, this is the accuracy level by which the person can, with this probability, I can say that the person is supposed to progress to the next level of the disease. So that is the main idea.
I appreciate that. Good start for application of machine learning to these areas. Good.
Okay.
Thank you.
Okay, thank you, sir.
Dr. Anish. Yeah.
Hello, sir. Hello, sir.
Yeah. Sarah join. Yeah, Shina Sarah join.
Yes.
Shina Sarah join, na?
Sorry, hello. Singh sir.
Shina Sarah join. No.
Hello.
Yeah, maybe some technical problem. Any question from the audience, please? Okay. Yeah, I think Shina sir has joined, I believe so. Shina sir, you joined?
Yeah, I have joined.
Yes, sir. Yeah,
Okay.
please, sir. Any observation, sir? Thank you. Hello.
No, it's okay. But one more thing I would like to ask the speaker. What is state of the art? Just in a few words. What is current state of the art?
Yeah.
The current state of the art includes application of fMRI along with the other modalities. The single modality will not give you so much classification accuracy. So as the proposed model says, I'm trying to incorporate more than one modalities into the work so that the accuracy can be improved.
Okay, that is about the modality. But what about the methodology?
Sir, they are using CNN. Yeah, they are using, in the case of techniques, machine learning and AI, they are using support vector machine and logistic regression rigorously. So I am using, we are in the next phase. In the next phase, I have derived some results, good promising results with respect to CNN as well, right? Convolutional neural network, CNN.
Okay, thank you very much. That's all from my side. Thank you. Okay.
Yeah, thank you, sir, and thank you, Chetan, also really for giving a good extensive literature review on that. I hope so that this will really add on to the other members also. What is their current scenario? But before concluding, I just put one question, Chetan.
Yes, sir. Please. Yeah, please, sir.
Regarding you said classification, is it not? So people might have done classification. You are doing also, are you done, or you're planning to do some work on that? It is a literature survey, I believe. So is it not?
Right. It was literature survey. I have progressed some part. As the current state of the art, as the sir said, they are classifying among two classes, right? Most of the, if you see the research review papers, they are classifying among two classes, that is normal control and Alzheimer's disease. So actually there is a very thin line, there is a very thin boundary between the person who is sitting in between them. Normal control is easy to identify. The person who does not have disease, it's very easy to say that the person is not having any disease. And the person who is already having some symptoms, right? Those who are entered into the state of dementia and all, we can simply by looking at the people, we can say that it is a person with a dementia, right? Alzheimer's disease present, right? So the actual logic and the actual beauty of the work lies in identifying those changes in the early state as possible as thing, right? So if I can classify,
that is missing from the previous literature review, is it?
It is missing, and the work till now does not incorporate all three classes classification among three states. So it is a two-state classification. I'm trying to have a three-state classifier, which classifies among three classes.
Yeah, thank you, Chitan. Really wonderful work you've done. The good
Thank you very
effort. We appreciate you. Really proceed and give a good shape on that. Okay, I think it will be valuable to the entire community, entire society. Okay. This
Thank you very much, sir.
there is no question from the audience side. Really, we are all thankful from the NIT Silchar fraternity that you all really joined to these sessions and shared your that hard working that you've done over the time. Thank you for joining. Thank you.
Thank you very much, sir. Thank you for providing the platform as well for such a nice environment and such a nice community platform is there. Thank you.
Yeah, thankful. Thank you to the. We are all thankful to you, really. Now I'll move over to Onish to invite our next participants or delegates.
Hello, sir. May I beg your pardon if we restrict our presentation to 8 to 10 minutes and the questioning to 2 minutes because we are running out of time.
Yeah.
So we have remaining 5 papers. So
still 5 papers, Onish? Still 5 papers left.
Yes. And we have, sir, next session is 3:15. So if we possible to be completing presentation.
Yeah. Please.
Okay. Next paper ID 19. The impact of visual representation of audio signals for Indian language identification. Writer Himanish Shekhar Das and Pinky Roy.
Okay.
Himanish.
Yes, sir. Good afternoon, sir.
Hello, Himanish. Where are you right now?
Right now I'm in Guwahati, and it's been a while that I've been tested positive. So right now I'm in home isolation.
Okay. So all the best. Okay. You joined to what university, I believe?
Sir, Cotton University.
Cotton University.
Yes.
Very good that you are our BTech. So Himanish is our BTech student, MTech student, also PhD. Now everything you have done?
No, sir. BTech and PhD. MTech from NIT Durgapur.
NIT?
Durgapur.
Anywhere. It is a NIT fraternity, na?
Yes, sir. Okay. Good afternoon, everyone. Without taking much time, I will just start with my presentation. So this is basically one of my PhD work. That is the impact of visual representation of audio signals for Indian language identification. Now, in today's presentation outline, I'll see out the introduction, the motivation behind this work, the related works that have been done till now, database description and the evaluation metrics, the proposed methodology, then experiments, result, discussion, and the contribution of this particular work with the conclusion, and we will see the references. Now, regarding this introduction, so basically what do we mean by language identification is that, so language identification is a technique to quickly and accurately identify the language being spoken. So it has two parts, basically the front end, where we extract the features from the speech signals, and the back end, which is the classification technique. Now, to extract the features, there are various levels of feature like acoustic, phonetic, prosodic, lexical, syntactic. But in generally, in language identification cases, we preferably use this low-level acoustic feature as well as the prosodic feature. Now, the motivation behind for this particular work is that it is the extension of the PhD work or the thesis entitled as Automatic Identification of Indian Languages based on various statistical approaches by my supervisor, Dr. Pinky Roy. So I'm now extending this particular work. So in 2013, my supervisor and her supervisor, they proposed a technique called a hybrid approach of vector quantization and a GMM-based approach. But in the era, right now, it is the era of artificial intelligence as well as the deep learning techniques. So in 2009, Jeffrey Hinton et al. Proposed deep learning algorithms, but these were not so much implemented in for the language identification. But if you see the trend, it's from 2015 or 16 onwards that has been changed. Now, since I'm extending that particular work and replacing those traditional techniques or statistical approaches, so in 2019 we have on 2019 and 20 we have proposed already a few works, but those works concentrated basically on the low level acoustic features or as well as the prosodic features. But now we are shifting on to this spectrogram images. So since convolutional from the deep neural network, when you are talking of deep neural network, that means we are focusing on deep features. Now focusing on deep features right now in each and every field, convolutional neural network is like grasping each and every aspect. So it is giving much more results. So can we just utilize those image features in our speech signals or not? So this is the perfect motivation for shifting from those low level acoustic features to visual features. So now in in terms of the related work, we can see this Montalvo et al. In 2015, in the first work, he proposed the spectrogram, where in the spectrogram, he just extracted the local phase quantization method, but in the back end, he uses support vector machine. But after a gap has been done, after a gap, then like in 2018 onwards, this spectrogram field has been occurred. So Ma et al. In 2018 has worked on AP17 to OLR2 database with the deep bottleneck feature, and they have extracted the equal error rate of like 10.04. So likewise in Mondol et al. In 2015, they have used some social media English Bengali mixed coded data from social media, and using word encoding, they have achieved 91.78% accuracy. Thereafter, seeing those tradition in 2019 and 20, we have also used some deep learning algorithms, but with the traditional features approaches, and we have achieved around 97.3 and 97.1% accuracy. In 2020 also, Deshwal and Chaudhary et al. They have also utilized this spectrogram and traditional or the MFCC or low level acoustic approaches, and they have also achieved like 94 or 96. So this work, for this particular work, we have used the old database, or I can say the in-house database that ma'am has already utilized in her PhD, and I'm extending that particular work. So in our database, we have total 5,000 training samples, in which 4,000 is your training sample and 1,000 your testing sample, and these are the sentences which are taken or they're being recorded to make the database. Like for Assamese, Bengali, Indian English, and Hindi. So basically, we have 4 classes. That means 4 languages. In terms of the evaluation metrics, we have taken 4 parameters: accuracy, precision, recall, F score. Sorry, 5 parameters, and equal error rate. So okay. Okay, so now the proposed methodology. In terms of the proposed methodology, this is basically the steps we have in the proposed methodology. Step one, first, step one, we just basically convert the spectrogram or the speech signal into the spectrogram images, and from those MEL spectrogram, not only the spectrogram, we have extracted the MEL spectrogram from the speech samples. From the MEL spectrograms, we have extracted the deep features, because our main purpose for this particular work is to see whether how much is the deep features or the deep features that we extract from the spectrograms versus the traditional or low level acoustic features, that is my MEL frequency substance coefficient feature. So the step one is to convert the spectrograms from speech signals. Then we have to extract the deep feature from the spectrograms using pre-trained neural network. In the third step, we feed those, whatever the extracted feature we have fetched from the spectrograms, we fetch them to different types of algorithms. So first one is the softmax regression algorithm, which is generally being used in the back end of the CNN approaches. Then we have the machine learning algorithm called random forest and SVM. So then we, and the end of it, the final step is like comparison between the traditional feature result and as well as the deep feature result. So the first thing that we have done is to extract the MEL spectrum representation. It is nothing but what spectrogram means is a visual representation of frequency spectrum in a sound or other signal concerning time is known as the spectrogram. So we have depicted the few sample spectrogram images from these 4 languages: Assamese, Bengali, Indian English, and Hindi. And why we call this MEL scale? Because as per this equation says, we generally, after extracting the DFT, so whatever the spectrum we receive, on that particular spectrum, we amplify the MEL frequency scale. So MEL frequency scale is nothing but a linear frequency which spaces below 1000 hertz and logarithmically which spaces above 1000 hertz. Okay. So generally in low frequency ranges, we generally have the most important information from the speech signal. Then we have the deep feature extraction using this pre-trained convolutional neural network. When we are talking about the pre-trained, since as we saw that we have only the total 5,000 sample data, we don't have that much of data. So that is why we have taken, okay, not exactly a huge network, but not exactly a small network, a VG16, where we have utilized the 13 layers, and specifically we have used the transfer learning approach. Transfer learning in the sense is that we can achieve transfer learning in 2 ways. transfer learning by feature extraction or transfer learning by fine tuning. For this particular work, we have used this transfer learning for only the feature extraction. That means we are going to take the extraction of those particular features before the fully connected layers. So till that connected layer, fully connected layer, we did not have to train this particular system. The model is already built. We need to just take the features out for our particular data. So that in that way we can reduce the complexity of the model, or I can say the time consumption for training. So from this particular feature extraction, we, as we say, that 70 to 70 to 512 number of features, if you multiply with 4,000 samples, so this much of features that we generally extract, and those features has been fed into softmax regression, random forest, and SVM with the default parameters. A softmax regression, we have the 4 classes since we have 4 languages, and these are the experimental results where we have fetched the confusion matrices for each and every aspect. So first one is for confusion matrix for CNN plus softmax and MFCC plus softmax. Then we have the CNN plus random forest. Then again for MFCC. And then we have the CNN plus SVM and MFCC. So basically, we are comparing whether the D feature is outperforming the MFCC feature, or is just there is some drastic difference is there or not. So from this accuracy from the table D, E, F, we can see in table D that we have the language recognition for SMS language for CNN SVM is 97.6, wherever for MCC and SVM we are getting 89.5. Likewise for Bengali, English, Hindi, we have different types of accuracies. Now these accuracies, or for a particular language, we can't say that why this particular language is being given more accuracy. So basically language identification is two types. One is the non-computational, one is the computational. In the non-computational matter, people generally work with the syllables and lexicon and all, but in the computational feature, we are only look for the statistical techniques. Okay, so in general we call the overall accuracy from this confusion matrices. So basically these are the result for F measure and the equivalent rate that we have achieved for this particular model or the particular approach. Now the experimental result and the discussion part that we can see from this approach is that experimental result said that table DEFG infers that SVM achieves better result with deep feature extracted from spectrogram images in X compared to MFCC. Now why SVM? So basically generally SVM is good for like when we have a little bit of good amount of features. Okay, then we have the table ABC. This table ABC, these are the first 3 confusion metrics. So as an overall the accuracy level that we can define for this particular model is from those 3 confusion matrices, and we have achieved 96.50% accuracy for CNN plus SVM, 94.80 for CNN plus random forest, and CNN plus softmax having 93.90. So basically the contribution of this particular work is to development of the CNN based softmax regression approach. So we can see whether utilizing conventional neural network and extracting the features with the other types of algorithms, how our model and the particular in-house database works. And second thing is the analyzing the benefits of this small scale network. We are not going for any large scale network like DenseNet and all. So in a middle structure like VGGNet, neural network. So how much accuracy generally we achieve? And finally, the final target is like improvement of language identification using some machine learning algorithm with the deep features. Now, in terms of the conclusion, whatever we have seen is the impact of this image-based feature for Indian language identification. Second is the comparison between handcrafted feature and the deep feature. Third is the 96.50 accuracy that we have achieved. And fourth one is SVM performs better with the deep feature. And these are the references. Now, based on this particular research work, and we have extended this work and have also proposed an enhanced model, and that has been in Applied Acoustics Journal, which is under review for 4 months. So thank you for this opportunity. Thank you, everyone. With this, I'll conclude my presentation.
Thank you, Himanish.
Thank you, sir.
Then I'll move to our Shina sir. Shina sir is there? Shina sir?
Yeah, I'm here. Yeah. So, one question is there.
Yes,
what is the computational overhead for this work that you have proposed?
Sir, the computational overhead in the sense, sir, basically, I have reduced this computational overhead in terms of this part. Basically, what the computational overhead is like, initially you have to extract the feature, then you have to feed into some some machine learning algorithms. But if we are working on some end-to-end approaches, like in case if I extract the deep feature from the network itself and use this online software execution part, so computational overhead will be less. So what we have done in this particular work, I have this overhead that I have to utilize in hybrid approach. So in our next approach, we have that I have already proposed. So in that approach, we have removed this computational overhead.
Yeah, so you have used pre-trained model for feature section, and after
Yes,
that
sir.
you have used
Yes,
other
sir.
classifiers.
Yes, sir. Yes, sir. So only I
Yeah,
have
yeah,
used the transfer learning for only this feature extraction part in this particular work.
yeah, 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 yeah. Oh, no, nice work. Good, good, very good.
Thank you, sir. Thank you, sir.
Okay, that's all from my side.
Yeah.
Thank you.
Yeah, thank you, sir. Thank you, sir, Shina sir, for available suggestions to Himanish. Himanish, just one question because already
Yes,
time is we're running out of time.
yes,
That
sir.
what are the features that you thought of in terms of speech signal? Can you just give
So,
few features a name? What are the
yes, sir.
features you want to mean?
So as in this particular slide, you can easily see that I have mentioned that there are lots of features. Like you have
Yeah.
the acoustic feature, the ML frequency, substrate coefficient, the PLP, this SDC. So generally we use in the if you are working in the low level acoustic feature, generally we take MCC and as well as the temporal feature, because speech is nothing but the time series signal, and for like sequence to sequence translation we have to use the temporal features.
Okay.
So
Thank you.
now
Thank you,
if you
Ananda.
work, okay,
Himanish, thank you.
okay,
Thank you.
okay, sir.
Okay.
Okay, sir. Okay, thank you,
Then
sir.
thank
Thank you,
you,
everyone.
Team Himanish and Dr. Pinky Roy also.
Thank you, sir. Thanks a lot, everyone.
Thank you. Thank you. Now, what to Dr. Onish? Please invite the next participant.
Move to next paper, paper ID 22, Musical Signal Processing, a Literature Survey, writer Omullo Sri Ulijala and Suryakant V. Gange Shetty. Could you please share the screen?
Yes, sir. Sir, hope you are seeing my screen.
Is not visible. Could you go to?
Sir,
Yes, yes.
a very good afternoon to one and all. Hope I'm audible and my screen is visible to everyone, right?
Yes, it's visible.
Good afternoon to everyone. I'm Amulya Sri and I'm a MS by research student working in International Institute of Information Technology. I was doing my research under Dr. Suryakant V. Gangashetty. We are a close knit of music students, I mean, music signal processing students working on music area and Triple IT Hyderabad. We basically work on audio thumbnailing and Carnatic music for the first time ever. And coming to a presentation outline, this is how it goes. First, I'll explain the objective and the motivation of how it actually formed, and then introduction of the classical music and the elements that are existing in the Carnatic music, and in what are all the elements that come across in the Carnatic concert, and the classification of Indian musical instruments and the areas of research. Basically, as part of this paper, I was explaining you the various areas of research in the area of musical signal processing. As we all know, music has become a very integral part of our lives today.
Hello.
Ha, sir.
If you can make your
Hello.
screen full screen, it will be better.
Full screen, sir. Okay, sir.
Your voice is not clear to us.
Sir, as we all, sir.
Now it's better, I believe. Yeah, yeah.
Hello?
Please proceed.
Oh, thank you, sir. As we all know, music has become a very integral part of our lives today. And with the digital revolution that has struck the world, and with the growth of the computational power, browsing and storage has really become accessible and effective. And the storage and browsing being accessible has paved a new way or an emerging area it opened a way for new areas of research. And when it comes to audio signal processing and in specific musical signal processing, we have a lot of areas such as synthesis of music, transcription, classification, and even in classification we have raga classification, tala classification, instrument classification, voice identification, audio matching, source separation, tonic identification, intonation analysis, melody analysis, rhythmic analysis, emotion recognition, thumbnailing, etc. Basically, as part of this presentation, I would like to give an overview of all the existing areas of music signal processing, primarily focusing on Indian classical music. And now, before going into further details of the areas, I would like to present a very brief idea of what Indian classical music is all about. And Indian classical music, the moment we say Indian classical music, it is always like Hindustani and Carnatic. Hindustani belongs to the northern side of the India, and Carnatic belongs to the southern part of India. And the oldest available books with respect to the Indian classical music are Bharata's Natya Shastra and Sarangadev's Sangeeta Ratnakara, which is way back to 10 BC. As a professor was telling yesterday in his presentation about these, the primary aspects of any music, any Indian classical music is about swara, raga, and tala. And uh, when we compare the Indian classical music with the Western classical music, one very important concept is like tonic, tonic or the shruti, what we call. Hindustani music is mostly what I said and preferred in northern part of the country, but Carnatic belongs to southern part of the region. Any music, whether it be it a Hindustani or a Carnatic, has 7 swaras, which is known as a saptaswara. But as part of this particular paper, I was only dealing with Indian classical Carnatic music. And now, as I told, the important elements of Carnatic music are raga, swara, and tala. When I come to swara, what is a swara is all about? Swara is nothing but a sound. In Indian music, we have something called as 7 swaras. We call sapta swaras. Sapta refers to 7. Actually, there are total 22 swaras, of which only 16 are what we are using. And the mythological origin, as an Indian, we always have this mythological origin of how did it come into picture. The mythological origin of these swaras is very interesting. Some say that this mythological origin has come from is associated with the call of an animal, and sa has come from the peacock, and the pitch of a re. The frequency of re has come from a bull, ga is from a goat, ma from a heron, and the pa is from a cuckoo, and da is from a horse, and ni from an elephant. However, there is one more mythological story which is very interesting, and which says that Lord Shiva addressed the congregation, and the differences that existed in his tone has become the 7 swaras. The Shiva, whatever addressed first the audience who are at the center, and then addressed the left and the right. That is why we call pa as what the audience who, with Shiva, with which intonation he addressed the audience at the center, is referred to the frequency of pa, and the left are this ma, ga, ri, sa, and the right are this da and mi. This is very, Bharata's Natya Shastra book actually explains origin of swara, something like this. And the other important element of Carnatic music or any classical music is raga. What is raga? And the book says raga is Ranjayati Iti Raga. It defines raga as Ranjayati Iti Ragaha. That which pleases to the ear is nothing but a raga. And ragas are being classified as Melakarta and Janya ragas. And there is also one other classification of ragas, which is Sampurna and Asampurna ragas. Sampurna raga is something which has all the swaras in both Arohan and Avrohan, while Asampurnas, if we miss one of the swara in either Arohan or Avarohan, we call it as Asampurna ragas. And then let me explain the other important aspect of Carnatic music, any classical music for that matter, is tala. Tala is a strong addiction of rhythm. In Carnatic music, we have talas, namely Adi Tala, Rupaka Tala, etc., etc. But how did the word tala has come into existence? As a combination of the first letters of Tandava and Lasya. Ta and La. Tandava and Lasya is what gives us tala. Tandava is nothing but the dance of the Lord Shiva, and Lasya is a dance of concert Shakti. Thus, the tala is a combination of energy and grace. Tala has no reference in the earliest system of music. We call the earliest system of music as Samagana. However, the Natya Shastra of Bharata and Sangeeta Ratnakara mentions the information about tala. They says that tala is characterized by 10 features, often known as tala dasapranas, what we call. There are I mean, any tala, we describe the tala using these dasa pranas. When I say dasa pranas, dasa is nothing but 10. Anga, Jati, Kriya, Graha, Marga, Kala, Laya, and Eti. What is Anga? Anga is a part of a tala or a limb of a tala. Jati is a kind of tala. How many laghus are there? How many angas are there is what Jati says. Kriya is action. Graha is described when the song has to comment. Not be at the beginning, but in the tala, when are you starting the song is what Graha describes. Marga is nothing but a path. It describes the duration of the action. And Kala denotes the number of matras in which it is being subdivided. And if I go internal details of all these dasapranas, it is quite extensive. So one other very famous system of tala is the Sapta Tala system, which is very, very famous in Carnatic music. And a total of 175 talas are there in Carnatic music. And now this is what is a very fundamental difference that existed between Indian classical music and a Western music. When it comes to the Indian classical music, this tonic has a very, very important, in fact, it is a fundamental concept of the Indian classical music. It is a pitch chosen by the performer, which is a constant throughout the concert. And in fact, it acts as a reference frequency, what we call as a fundamental or a reference frequency in computer science terminology. And now, why is it different from Indian classical music and Western music? Suppose in any Indian classical music, I can take my own tonic. I mean, my own tonic differs from the other singer's tonic, right? That is how a tonic concept becomes very, very fundamental. And to do any kind of analysis, processing, first we have to often the swara sa is considered as tonic. And how do we recognize a tonic? In any Carnatic concert, if you see, there will always be something called as a tambura at the background, who is some artists would be playing it to establish the tonic in any Carnatic music. I mean, scientific terms, it is a linear shift on time frequency graph. And now, how does a Carnatic concert goes? In any Carnatic music concert, the emphasis will always be on a vocal music or a singer. From the perspective of the listener, the Carnatic concert is more like a storytelling or the conversation between the artist and the audience. There is no definitive structure. However, people conventionally they start with a varnam and a kriti. A varnam is nothing but a warm-up kind of work which sets the mood of the concert. And now, when it comes to the main musical concert, it will basically be as a ragam, tanam, pallavi, and all. And however, it ends with a mangalam. Mangalam is nothing but which says that this concert is almost to an end. This is how any Carnatic concert goes. How does a Carnatic concert go? It is basically a kind of storytelling. And now, when it comes to the
madam,
classical instruments, sir.
Yeah,
Sir.
you please be in the time frame, please. Okay.
Yes, sir. Yes, sir. These are all the classification of Indian musical instruments. For the first time, the classification of instruments is being done by Hornstall way back. However, according to this Hornbostel fact system, the instrument can be classified as three types: codophones, aerophones, and idiophones, as I told here. In detail, these are all the classification of Indian musical instruments. And now, when it comes to the actual areas of research, there are various areas of research. This section actually gives an overview of analysis methodologies involved in the music signal processing. And now there are various areas of research, as I told earlier: source separation, emotion recognition, tonic identification, intonation, rhythmic analysis, ontologies, automatic music stretching, emotion recognition, note representation, raga identification, tala identification. I'll explain each of these details in a very, very briefly. When it comes to source separation, what source separation is all about is, suppose there is a concert. How do you separate vocal signal and an instrument signal is what source separation is all about. And there is also one more category in source separation. How do you separate instrument? Suppose I play veena and a violin together. How do I separate veena and violin? That is also a part of source separation. There are various methodologies that are used: harmonic structure, Bayesian harmonic model, coherent modulation, spectral filtering, regression models, Gaussian models, non-negative matrix factorization, repetitive, and all this. There are extensive amount of research that have gone into source separation. That these PCA, Fourier transforms, spectral inversion, repeating musical structure. All these are part of, research has been done in so. And now when it comes to emotion recognition, this is another major area in music signal processing that has become popular and very recent areas. And papers have described, and literature has described a novel methods estimating these emotions by a piece of music from its acoustic signal. The focus of these emotion recognition is based on multi-stage recognition these days. After the training, the regression happens in a predefined way and can be adopted to an acoustic signals in a different musical properties. And along these, there are, these days in recent years, the focus is being on music stage, multi-stage recognition. However, extensive literature is there on emotion recognition on Gaussian models. Gaussian models, basically, they are two stages. They extract the features and then they classify. In the first stage, the feature set can be rhythm, dynamics, timbre, pitch, tonality, etc. And in the second stage classification, they were, generally literature have done statistical parameters such as mean, standard deviation, etc. They have used in the and have performed emotion recognition. And now Thala recognition is one another very famous problem in music information retrieval. And this is unseen problem as well. In Thala recognition, literature used both statistical and as well as a deep learning techniques using CNN and RNN. And a new research wing is coming with respect to audio thumbnailing. Audio thumbnailing is nothing but, when it comes to audio thumbnailing, thumbnail is nothing but a preview of the entire audio. Instead of hearing to the entire audio, I hear to a thumbnail and then do all my processing on the thumbnail instead of the complete. This concept of audio thumbnailing is coming with respect to Thala classification and with respect to Raga classification as well. The other areas of music signal processing are intonation rhythmic analysis using pitch value distribution, data-driven approaches. There are so many data-driven approaches which literature has mentioned. Intonation in the sense, how am I speaking? How is the singer actually singing? How is the rhythm? How is the thala? How many number of beats are there in respective song? All these research have been going on. And with respect to tonic identification for any classical music in India, we have to identify the tonic and then we go forward. And then raga classification, there are so many methodologies with respect to raga classification as well. And now this presentation
you are requested to wind up, please.
Brief introduction of all these methodologies. As I told it. Hello.
Madam,
sir?
Could you briefly explain?
Am I audible, sir?
Yes, madam. It is audible, but could you make it briefly explain? Hello.
Hello.
It's audible. Could you make it briefly explain this part? We are running out of time.
Yes, sir. Last slide, sir.
Yes.
However, whatever techniques I have mentioned above are not the end of music signal processing. There are many open challenges and there are open exciting problems. We hope these developments continue and lessen the gap between how human and machine perception takes place and make music more colorful. Thank you. Thank you. That's all from my side, sir.
Mushroom, sir?
No questions from my side, sir. It's okay.
Sir. Thank you, sir. Sir, Mushroom, sir, any question?
I have one question.
I have no question, please. Okay.
Okay, sir.
Thank you. Thank you, madam. Thank you, entire group. Thank you.
Yes,
yeah, thanks for letting me ask. This is rather a remark. Thanks for the talk. It's very abstracted, so I'd like to hear some state-of-the-art results where the technology is currently. If you have any remarks, thank you.
Yes, sir. The current state-of-art technology is towards CNN and RNN, and it is like LSTM using CNN and RNN. We were able to achieve quite a good number of accuracy with respect to raga, thala classification using thumbnailing. When it comes to thumbnailing is something which is very boom kind of thing in music signal processing nowadays. And as part of IT group, I can say that we were able to achieve 92% of accuracy using CNN, RNN, and raga and thala classification.
And what is the data set, please?
The data set is a open data set which is given by Comp Music. Comp Music is a project, sir.
Yeah, I am a part of
It is an
Comp
open
Music, so I
data
know
set.
that.
Oh,
So,
okay, sir. Oh, good, sir. We were using that data set only.
okay. And do you have any applications of the thumbnail? For example, summarizing the concerts and sharing that somewhere? I'd like to just take a look. It's exciting results that you have achieved so far.
And Tala classification is what we have results. Raga classification we did not get published, sir. Tala classification, there were exciting results, I can say. We have presented a couple of
Okay,
papers
thanks for
last
this.
month.
I should go to your paper and see the detailed
Yes,
results. Thanks.
yes.
Okay, okay, thank you. We are moving to the next paper, paper ID 23. So, audio quality control method based on audio secret sharing. Authors Sachin Kumar Singh and M. Yadav. Could you share the screen?
Yeah, so just sharing the screen.
So please restrict the presentation within the time bound.
Okay, okay, okay.
Okay, thank you.
Is it visible?
Yes, visible. Go ahead.
A very good afternoon to session chair and all the members of FRSM 2020. And I am Sachin Kumar Singh. I'm here to present my paper, which is audio quality control method based on ASS, that is audio secret sharing. My paper ID is 23, and I have done this work with my professor, Mr. Manager Yadav. So I'll be starting with.
Can you give full screen? Full screen?
Yes, sir. It is full screen.
Okay. So it's full screen now?
Yes, yes, go ahead.
Yes, it is fine.
Yeah, so I'll be starting with introduction to visual cryptography, and then I'll be moving on like it is based on visual cryptography, and then I'll be moving on for audio secret sharing, and I'll be ending with discussing the result of my research. So first of all, I would like to talk about visual cryptography. Visual cryptography is just an classical approach for dividing any secret image into two or more parts in such a way that if you are taking only one part, it reveals nothing, but when you combine these two, you will get the original secret. So the breaking of the original secret is known as encryption, and getting the original image back is known as decryption or reconstruction. So basically, it started in the beginning, people applied this to only images, and as the time proceeded, people started applying it to audios as well. So this is an example like how a share can be generated and how we combine it. When we combine it, like you can see, we just get the original secret back. In here it is Wikipedia. So with the advancement of time, people applied this scheme to audios, and then it called it audio secret sharing, in which an audio is divided into many parts and it is recombined to get the original audio. So like there's a classical example, like we are just trying to embed 0, 0 and 1 here, and we are doing it in this cover audio, and we are generating share 1 and share 2, and when we are combining it, we are getting this signal back here. This is 0, 0 and 1. So this was the basic of what is audio secret sharing. So basically, when we talk about an audio, what happens if I combine two different audio signals, and like one have amplitude of B, an array of amplitude B, and another has got the array of amplitude C, and we combine it and we get a like
constant value, some constant value, so it magnifies the amplitude or it decreases the amplitude. In this only happens when we multiply or divide the whole array with a constant number. This is not going to happen when we multiply or
Yeah,
divide.
hello.
Yeah.
Please be in the time frame, okay?
Yeah,
We
yeah,
are
sir.
already
I'll be.
really
Yeah,
running.
sure, sure. Yeah, I got it. Sir. Yeah, so I was saying, so here we are considering audio as a array of amplitudes, and when we divide the whole array with a constant number, if we divide it, the audio quality decreases or the audio volume decreases, and if you multiply it, amplifies. This happens when we multiply with this constant number to all the elements in the array, but if we divide it with different numbers, the result will be different. And my approach is based on this particular idea. So in my proposed approach, we take an audio signal, we convert the audio signal in a stream of amplitudes, that's an array. We determine the neutral range, we determine the degrading factor, and we get two shares. One is low quality share, that is the low quality audio, and another is called quality share. Quality share is responsible, and when we combine the quality share with low quality share, we just get the original audio back. So if you talk about the neutral range, like if I'm saying in one audio signal, if there is silence somewhere, so obviously if I am degrading the quality, the silence should remain silence. If there is a place in an array which consists of zero amplitude, and if I put a value of 10, 20 or 100 there, it will become very noisy. So that's the role of neutral range, in which we do not disturb the amplitude where the amplitude is zero. Degrading factor is kind of considered a factor which lies between 0 to 1. The amount of degradation you want to do with the audio is degrading factor. And for reconstructing the audio, we just combine these two generated share and we get the reconstructed audio back. So I just told that neutral range is the range in which we are not going to do any changes, and degrading factor is a factor which we decide for doing how much we want to degrade the audio. And it generates two shares, low quality share and quality share. So like this is a small quick example. Like this is the original stream of amplitudes here, and we just take a degrading factor of this, and this will be completely random. And neutral range, like if this is in neutral range, I'm not going to change anything in low quality share, and we'll put 0 in quality share. For the other one, what I will do, I will multiply this amplitude to the degrading factor and put it in the quality share, and the remaining will be in the low quality share. And that's how this algorithm works. And then this share that is generated will be a low quality share, and this share will help us in reconstructing the original audio. So for my experiment, I use Indic TTS database that provide audio files for which are also live in 13 different languages. And for performance measures, I have used some subjective and some objective measures for evaluating our performance. I have used mean opinion score, comparison mean opinion score, and perceptual evaluation of speech quality, which is ITU standard. And now, like, these are just the labels that if in CMOS rating I get a 3, that is very good, and if I get -3, that is extremely worst. And in label I get excellent and bad. So what will happen for original audio and low quality audio? The result should be slightly good or slightly worse. Then it will signify that the low quality audio is actually low as compared to the original audio. So what is so this is the experiment. Like, this was the original audio file, this was the low quality share, this was the quality share, and when these two are combined, then we get the original audio back, which is also known as reconstructed audio here. And like if we go through those experiment results, so PESQ is it comes to be 4.50 and 4.99. It shows that for the reconstructed audio, the quality doesn't degrade. CMOS come to be 0 and 0.1, which is about the same. It means because we have chosen very low quality degradation, the audio quality has degraded. and then after. So, and they like these are some approaches, previous approaches, which were of audio secret sharing. But as you can see, there was no previous approach. Like there was no approach in which the audio secret sharing concept was applied for quality control, and we have applied it on call for quality control. And now, okay, this is an example of why neutral range is very crucial. As you can see, like these amplitudes, they have like they are quite of silence. If you do not use neutral range, that silence will become this enormous noise. That's why we are using neutral range. And and its application can be like, today there are a lot of platforms for music streaming, audio ebooks, so they can provide the low quality songs or low quality ebooks for free, and they can charge for the good quality. So it can be implemented to audiobooks and music streaming platforms. And I would like to conclude that in the experiment, it shows that the audio get degraded, and it has been seen by the subjective and objective parameters. And this technique can be used for audio quality control measures for the unprecedented platforms. And thank you.
Singh sir?
Yeah, one or two questions.
Yes, sir.
What are the techniques that have been used here? You must
What I did not got you, sir. Can you please repeat, sir?
performance metrics.
Oh, performance. Yes, sir. I have used PSQ, which is ITU standard, and I have used mean opinion score, in which the audio is played in with a group of people, and they rate it on the scale of 5 or 3.
What about PSNR?
No, sir. I have not used PSNR. I was using PSQ as objective parameter, so I didn't use PSNR.
Okay, okay, okay. Thank you. That's all.
Okay, thank you.
Yeah. Anish, any question from audience?
Yes, one question, sir.
Yes, sir.
Usually in visual cryptography, we used to have tiers, tiers 1, tier 2, okay? So
Sir.
in this technique of yours, so how many tiers you are producing?
Sir, I have as much you want, number of shares can be produced, but for illustration purpose, I have only produced 2 shares.
Okay, how about the time complexity when you increase the share?
It's if you go about like big O n, that is order of n, and I have worked in like 15 seconds of audio, get a share constructed in 0.7 seconds.
This share that you produce, are they audible to humans or are they totally chaotic?
The low quality share is audible, but its quality is low, like there's a kind of noise in it, and the quality share is completely inaudible, like it's complete noise.
See, in images, if you apply visual cryptography, then we see it turns out to be totally chaotic. But in audio, we are not. We are saying that we are not getting a chaotic type of audio. Why is there difference?
What's sir? Can you please repeat your question?
That if we are applying visual cryptography in an image, those two shares are totally unvisible to anyone. You getting me?
When we apply visual cryptography, the shares are invisible.
Means not, we are not able to understand that. For example, the first image that we saw regarding Lena, those two
Yeah,
shares,
yeah.
we can't find out anything relevant to Lena.
Yeah.
But when you apply an audio, you are saying that the shares that we produce are audible. You can understand.
Yes, because like the intent of this work is to control the quality of an audio. I can also make the second share also inaudible, but that will all ruin the purpose of this paper.
Okay.
Yeah.
Okay. Thank you.
Okay. Thank you.
Okay, move on to the next paper. Paper ID 29. Speech-based emotion detection using R. Writer Subarna Chatterjee and Nida Fardin.
Yes, sir.
Could you share the screen?
Yes, sir. So it is audible? Hello?
Yes, yes, go ahead.
Okay. Paper ID 29, the title is Speech-Based Emotion Detection Using Art. Myself, Subarna Chatterjee from Department of CSC, Ramayana University of Applied Science, Bangalore. The work is done by my student, Nida Farhin, and I'm the co-author. So today I'm presenting the paper. I'm directly going to the introductions. So here, introductions. The human-computer interaction issue is a challenging issue to interpret and recognize speech with emotions. Human speech contains qualitative and quantitative features that can be extracted by speech processing. Speaker's emotion can be recognized using text mining approach on audio files when the audio files is converted to text. It looks easy for a human to understand and identify the emotions of an audio file.
Your sound is not clear. Madam, your sound is not clear. Can you make it more louder?
It is coming clearly? Hello?
Okay. Please proceed.
So speaker emotion can be
Please proceed.
recognized using... Okay, sir. So it looks easy for a human to understand and identify the emotions of an audio file, but average score of detecting different emotions is between 56 to 85%. Different emotion states can be recognized using the characteristics, speech, energy, LPCC, MFCC, and LPC-MCC coefficients. Many have analyzed and differentiate different fusion of features. Now here the methodology, what we have applied. Datasets. The real-time audio samples are taken from an open web source called OpenSLR. 4 datasets are downloaded. Each of the datasets represents one emotions. Dataset 1 represents angry emotion, dataset 2 happy, dataset 3 neutral, and dataset 4 sad emotions. Each of the 4 datasets has 50 samples of audio waves of emotions spoken in Javanese, a native Indonesian language. Now the methods. The model developed for this problem has 3 parts. First, the pre-processing of the audio samples. Second, train the samples. And third, to test the samples for accuracy predictions. Now read the audio files. So proposed algorithm for emotion detections. Step 1 is read the audio files. Here we have used art tools to implement the algorithm. So list files and read waves functions are used to read the audio files. This is done for
one
data sets.
instruction, hello, to the speaker, please. As we are running shortage of time, our next session is 3:30. Already, I think we are in 3:30. A few more papers still on the pipeline. Please quickly wind up summary wise. We will be giving you 5 to 7 minutes after the question hour. Can you?
Okay. Yeah.
Sir,
Yes,
actually,
yes.
Please.
Sir, actually, we have 3:15, the next session.
Okay, we will do. So next step is data pre-processing. So here we are using Hamming window for pre-processing. Now feature extractions. So feature extractions, here we have used echo-stat function is used for feature extractions of the audio waves. And here it used the principle of short-term Fourier transform, and that converts the audio wave into frequency and time domain matrix. And the matrix will have time and frequency curve. Each curve will represent probability mass functions and is transformed into cumulative distributed functions. From CDF functions, median, initial percentile, terminal percentile, and interpercentile range are measured. P1, P2, and IPR have specified as fraction parameters. The functions return 10 items, and from these 10 items, 8 items we have chosen as the features. So 8 features has been chosen, that are time P1, time M, time P2, time IPR are calculated with respect to time, and frequency P1, frequency M, frequency P2, and frequency IPR are calculated with respect to frequency. Now data preparations. After all 8 important features are extracted from the datasets, the results we have 50 samples of 4 datasets having 8 features each gives a total of 50 by 4, 200 samples. So 200 rows by 8 columns is the total dimension of the datasets, that is 200 samples and 8 extracted features. Now output variable y is created to label the audio samples and added as the last column. Therefore, the new dimension of the whole datasets become 200 by 9. Dataset 1 angry represents emotion angry is being assigned to class 1. Dataset 2 represents emotion happy is assigned to class 2, and dataset 3 represent emotion neutral is assigned to class 3, and dataset 4 represent emotion sad is assigned to class 4. The model, when trained and tested for classification, classified the datasets into respective classes. Now classification. 3 classification techniques are used here. They are CART, Canyon, and random forest. The dataset is partitioned into training and testing following the ratio 7:3. Using 70% of the data, that is out of 200 samples, 40 samples are used for training the classifier, and performance accuracy is checked by the statistical summary. If the accuracy is good, then the remaining 30% of the data is used for testing the model. Otherwise, some issues with the model and we need to change the model. Now analysis and results. Figure 1 shows the time, and figure 1 and 2 shows the time and frequency curve. Periodogram of each samples for dataset 1 represent angry and dataset 2 represent happy emotions. Figure 3 and 4 represents the periodogram curve of time and frequency of dataset 3 neutral emotions, and dataset 4 represents sad emotions. Now table 1 represents the confusion matrix, statistical summary, testing results of the classifier card calculated using R tool. The classification sensitivity specificity is coming good. And here this is for classifier KNN using R tool, and this is for random forest classifier using R tool. Now table 4 represents the comparison of the classifier CART, KNN, and random forest. Here we have measured accuracy and kappa value for doing the comparison between the classifier CART, KNN, and RF model. Now table shows best results for random forest classifier. Average accuracy for KNN classifier comes 88.16%, and CART classifier it is coming 98.71%, and for random forest average accuracy is 100%, and average kappa value for KNN is 84.1%, for CART it is 98.28%, and for random forest it is 100%. Now the algorithm is implemented using accosted function and short-term Fourier transform for emotion recognitions. Classifier KNN, CART, and random forest are used, and validations and analysis for each of the classifier are compared by measuring accuracy and statistic measure by mean, median, and kappa values. Now, feature scope of this work, using more robust algorithm, we can use more robust algorithms such as SPM, HMM, deep learning algorithm. Training can be done with deep neural network, and training classifier with more samples of larger data sets to check complexity, and more number of
features. Thank you, Shobana madam. Thank you.
These are the references.
Thank you. Any question? Yeah, sir is there. Hello. Our Shina sir is there.
Yeah, I'm here. So thank you, sir. No questions. Okay.
Yeah. Okay.
No questions.
Yeah. Any question from the audience, please? I hope so. There is no question. Then thank you to the Subhana Chatterjee and entire group really for giving their valuable work through the entire forums. I hope so that many people will be benefited out of it. Thank you, Subhana Chatterjee and entire groups. Now I want to Dr. Onish Kumar for inviting the next participant. Please, Dr. Onish, please.
Yes. We move to the next paper, last paper, paper ID 55, Indian language speech level, a de facto national standard. Writer Samudra Vijay K. Could you please share?
Good afternoon.
Yes, please.
Yeah, I start sharing. Can you see? Can you see?
Yes, sir. It is.
Thank you. So these days, interacting with the computer using voice mode has become prevalent. It's become common. We use search engines using voice mode, mostly in English, and a few other Indian languages also come into picture. So in the case of the interaction with the computers in voice mode, there is, you speak, the computer recognizes what you speak, and based on that text that is generated out of the speech, it interprets your intention, and from that intention, it will goes to the database, gets the appropriate answer, and can even speak out the answer. Therefore, voice interaction involves two major technologies. One is speech to text, another is text to speech. In both cases, if you look at the speech recognition, that is speech to text, automatic speech recognition, or ASR is the acronym. The traditional ASR, speech recognition system, employs statistical models of acoustic phonetic units. Acoustic phonetic units, examples are phones or phonemes. So, and speech is primarily a sequence of words, and each word can be treated as a sequence of phones. So there is a good correspondence between the speech and the phone sequence. Similarly, if you look at the text, the written language, a text is a sequence of characters, and in case of languages, scripts, Indian scripts, for example, there's a good correspondence between the character sequence and the phone sequence. Good correspondence between character and phone sequence. It is not perfect, but it's approximate. So in both cases, there is a concept of a phone, the basic unit. And the speech recognition needs the models of such acoustic phonetic units. It needs to be trained. Therefore, it requires training speech, not only the speech data, but also the corresponding word sequence and associated phone sequences. So these phone sequences, it is better if it is produced in the form of alphanumeric ASCII labels, so that it can be processed easily by computers. So this paper is about a scheme for ASCII labels for the sounds of the Indian languages. The acronym is ILSL, or Indian Language for Speech Labels. Whenever the acoustic phoneticians have studied speech sounds for quite some time, and they have come up with the scheme of representing different speech sounds using Latin alphabet and its variations. But Latin alphabet is not good enough to specify all speech sounds. Therefore, they use diacritic marks and modifications of the Latin script. For example, if you look at these a stop consonant, ta and ta, in addition to the ta, there are retroflex sounds, ta and da. So to distinguish between ta and ta, they use some kind of modification. Here, a hook here. This is a da, the normal D is da. Similarly, there are dental stops, apical stops, laminar stops. So you see that various markers are devised so that the speech sound is unambiguously represented in a graphical form. But that is good, but that is not convenient for it to process by computers. Computers prefer ASCII alphabetics, and because of that, such a scheme for representing different speech sounds of American English was generated, and that is called ARPABET instead of alphabet. ARPA stands for Advanced Research Project Agency, and this was done about 2-3 decades ago. And there is a existing pronunciation dictionary that lists each word in terms of the sequence of labels corresponding to the associated speech sounds. And Carnegie Mellon University has a dictionary which is used in various ASR systems. Such a scheme of representing speech sounds using Latin alphanumeric sequences is extended to European languages, and that is called SAMPA, Speech Assessment Methods Phonetic Alphabet. And that was primarily used by European languages for ASR, and it is extended to other, all the languages. It's represented the entire IPA chart, International Phonetic Alphabet, and that's called SAMPA. And it is extended to Chinese language, it's called SAMPA-C, and it has been used to recognize a spontaneous speech. If you look at the Indian scene, there has been some attempts to come up with some standards, and one of them is called ISKI. ISKI is Indian Script Code for Information Interchange, just like ASCII. It's the I stands for Indian, and that is a Roman transliteration of Indic scripts, and that is a national standard. But for speech recognition people, they are interested in representing not the script, but the spoken language, speech sounds, phonetics. And there have been attempts, for example, for Mumbai, established a speech database in 1990s, and that used a scheme which used only ASCII characters, upper and lowercase ASCII characters, A to Z, upper and lowercase, and also numerals. For example, the example of the scheme is I'm using the Devanagari script. Long A is uppercase A, and so on. And there were some schemes to denote the different acoustic segments, even in a single phone. For example, a stop consonant can have up to 4 distinct acoustic segments. Prominent of them is the closure, and then the release, frication, burst, and so on. So a stop consonant itself was denoted as a sequence of 2 labels, one for the closure, another for the release, frication, and burst, and so on. In fact, such a scheme is used by the paper that was presented yesterday by Ankit Kumar and Rajesh Agarwal, which used the TAFR database and other databases. Now, of course, individual researchers had their own scheme, but there was a need. Then, about 15 years ago, there was a ISR consortia, TTS consortia, sponsored by the Department of Electronics and Information Technology, DEITI, and similarly TTS consortia, text-to-speech consortia. So at that time, a common format for such labels of the Indian speech sounds was felt, and that gave rise to Indian language speech labels. I'm just going to talk about the schematic and the guidelines or the scheme guidelines behind designing such an Indian language speech label set. The idea is that since there are 2 points. One, Indian languages are fairly similar. Although their major 2 language families are Indo-Aryan and Dravidian. There are other 2 also, 3 also. And the script that is used by Indian languages, most scripts are derived from Brahmi script, and there is a similarity. Therefore, there's a lot of similarity in the sounds of the different Indian languages. So the goal was to give one label, single label, to similar sounds in different Indian languages. I say similar, not necessarily exactly same. And the label should be case insensitive, because when TFR devised such a label, they said uppercase, lowercase, but then Windows systems does not distinguish between these 2 things. There's a case sensitive. Therefore, we said the label should be case insensitive. Upper or lowercase, it doesn't matter, but preferably lowercase. And design the label set such that when you go from text characters, which may be native script, Devanagari or Tamil or whatever it is, to these label sequences, you should also be able to come back. The process should be nearly invertible. I'm saying nearly because there is the script to phone transformation. Although we think that Indian scripts are phonetic, they are nearly phonetic. There are one-to-many mappings. But this design label should be such that the native script should be largely recoverable from the transliteration. So a system of suffix to the label and also letter combinations were used for the labels. Here is the Devanagari alphabet used by many languages in India, Hindi and others. is shown here. In the blue, you see the letters of the Devanagari alphabet, and here are the corresponding matras too. And in the red, you see the ILS labels. And all labels in red are in lowercase. A is A, long A or with the longer duration is double A. So the first A letter A is repeated. Similarly, E and E and so on. Also, even if there is a matra, this matra represents the speech sound long A and so on. So E, O, A. Now, when you come to Dravidian languages, for example, there's a distinction between short A and long A. But that distinction is not in that form in Hindi, for example. The A here, this denoted by this script, is something between the short A of Dravidian languages and long A of Dravidian languages. Little more closer to long A. Therefore, this symbol double A is given here. Double E, E is given for the symbol A. And for this so-called long A, this is that of the kaise A. It is actually not single phone, but it's a diphthong. It is going from one vowel to another vowel, going from E to A, kaise. Therefore, it has a symbol A, I, E, I. And similarly, con, OU, and so on. Now, if you come to the consonants, there are stop consonants here in a 5x5 matrix. They are arranged according to the place of articulation, and some of the symbols are simple. Ka, and whenever there is a aspirated counterpart of ka, and this is ka. So aspiration, you have a suffix h. Similarly, ga, and the corresponding nasal n followed by the g, which is the voiced stop in the same place of articulation, the same. Similarly, affricate, cha, 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 and there is a ta and a ta. You need to distinguish. T is not sufficient. Therefore, we use the suffix x.
Excuse me, sir.
Let's go to summarize.
Hello. Yeah. I want to say that as we are running out of our time, can you wind up things in a better quickly so that because our next session is going to start very
I'll
soon.
take 2 minutes and finish. Okay, thank you.
Sir,
So
my appeal, please, sir. Okay.
Thank you. 2 minutes.
We'll be inviting you because we are very happy that in this age, really, we have so enthusiasm to really encourage other members to work on that. We'll be inviting you separately for that. Really, I'm very glad to see that in this age, really, you are presenting with so much energy. I'll be very happy to invite you, sir. Separate sessions for separate special invitation or special talk for this particular area. As we are running short of time, I request you, please, sir, just to have a quick wind up so that we can conclude and we can move to the next, sir. Okay, sir?
I'll take 2 minutes.
Okay, sir. Please, sir.
The details of that in the paper, I'll skip that. And this ILSL scheme has been designed, has been used for 16 languages, and they are listed here, and the corresponding labels are also there in the table. And there are certain special symbols have to be used to take care of some sounds, special sounds in some languages. For example, Assamese has a sound velar fricative, which has a symbol X, and so on. And in addition to that, there are, in addition to the major language families, Indo-Aryan and Dravidian, there are Tibeto-Burman languages, and many of these languages are tonal languages. So there are tone quality which distinguishes sounds, distinguishes words. So if I say ah with the, and instead of ah, I say ah or ah, then the meaning changes. Tones are minimal pair words with the, there are minimal pair words which change not in sounds, phones, but also in tones. So we have to give some suffixes to these symbols. For example, the 4 types of tones that are there in the various languages, these symbols are given something like this. And this scheme has been used by ASR consortium, also in more than a dozen languages, and also in TTS, text-to-speech consortium languages. And recently, the idea was that the whole purpose of this scheme was that language, we always have a problem of limited linguistic resources in India specifically. But if there is a common label scheme, then speech data that has been collected for one language can be used for another language. So that was the purpose of designing such a common scheme, label scheme, and it has been used. I'm glad to see that it has been used. For example, speech recognition of code switching speech, where Hindi was being spoken and English words are in between, comes in technical words, and the same ILSL scheme was used. To conclude, the idea was to design a common label set which used the phonetic nature of the Indian scripts, and the goal was to share linguistic resources for implementing speech systems, and that has, to some extent, it has been utilized by researchers, and it is used widely by a large number of people. Therefore, it is a large number of researchers in the speech and language community, and therefore it is a sort of de facto national standard. It's not yet a national standard. To become a national standard, it has to be extended to all the languages of the India, at least the major languages, Schedule 8 languages, and many other languages in this part of the team. And I'm happy that this particular scheme was not presented in any of the earlier conferences, although it has been being used for more than a decade. And I'm happy to present it in the Silver Jubilee of the FRSM conference, something that was started by Dr. A.K. Datta 3 decades ago. And I'm happy that it is being presented here. Thank you. End of my presentation.
Okay, thank you, sir. It's a nice presentation. So I'm thankful to the session chair for their valuable suggestions and enlightenment. This is a very nice session and presentation. So this is the concluding of our session, technical session 3, and we can move to technical session 4.
Okay. Good afternoon, Professor Devashish De and Professor Nidhu Sinha will be chairing the next session. Welcome.
Thank you. Thank you, Dr. Mitchell. Thank you very much. So I think we are already late by 30
minutes. We have to be a little bit fast.
Yeah. Okay, no problem. It happens in the conference. Doesn't matter.
Yes, I understand.
Yes, part of our life. And really, we are happy to be here, and this conference on speech and music is very, very important in context of India and the other countries. And I know personally, I worked with Ashok Kumar Datta of ISI Calcutta. So I'm associated with this FRSM for a long time. And so without wasting time, I just want to start our next session. So is the next paper the presenter is present?
Yes, sir. So we can go to the page, paper number ID 6, IFSC, a database for Indian folk songs classification. Authors A. Patel, A. Shah, K. Gaur, and S. Mankad.
Hello. Yeah, is my screen visible?
Yes, yes.
Yeah,
Visible.
okay. Yeah. Okay. Good afternoon to one and all present here. I am Anshul Patel, here to present you our paper titled IFSC, a database for Indian folk song classification. Moving on to the introduction. So India is a country rich of different cultures, each having their own identity. These cultures give rise.
Alignment is not okay. Just check the alignment. You have to unzoom it.
Yes, sir.
What's the focus of the paper is not okay. Focus means the alignment. At least to me, it's showing some parts. Right side is not visible. Yes, now it is okay. Now it is okay.
Okay.
Earlier it was okay.
So due to this different cultures in our India, it gives a rise to a wide variety of folk songs. We saw this as an opportunity to apply artificial intelligence to try classify these songs into their respective regions. However, to the best of our knowledge, there was no standard audio data set which represents Indian folk song classification songs from various regions. So in this paper, we have introduced a new data set for folk songs and demonstrated our machine learning approach for classifying the folk songs using the same database. So moving on to the literature survey, many of the music information retrieval tasks were directed towards genre-based audio classification, and that too on Western music dataset. However, no significant work was done, especially in the area of folk song classification. So
I think we cannot see your slide properly. Can you just align it properly?
Let me share the screen again, I think.
Yes.
Is it visible now? Hello.
No. Share your screen. Share screen. Now it is coming. Yes. Now it is okay. Perfect.
Yeah. Okay. So as I was saying, there are two main approaches for feature extraction in the literature. First one is the acoustic features, and the second one is the symbolic features. Moreover, there are two types of classification models that were used for such tasks. One is genre-based, and the other one is region-based. In our paper, we have focused on the region-based classification approach using the acoustic features only. So moving on to a detailed description of the literature survey. As you can see from the table, the paper cited as 18. The authors carried out an implementation on input audio with a data set of 495 Chinese songs. They have trained a support vector machine on the 12 basic acoustic features. In the next two papers, cited as 13 and 14, a similar approach of training a symbolic music feature density using extreme learning based approach has been taken on two separate datasets that are Chinese and German Austrian. In the same way, as you can see, wait a second. As you can see over here, the regions that were mostly used were not from the Indian subcontinent. So this motivated us to present a standard dataset that can be used for classifying the Indian folk songs based on their regions. Now I would like to introduce the dataset. So the dataset is been titled IFSC 5, which includes 307 songs taken from 5 major regions of India, namely Assamese, Uttarakhandi, Marathi, Kashmiri, and Kannada. The dataset was collected from publicly available sources and commercially available recordings. Most of these songs were collected in the WAV format with a sampling rate of 44.1 kHz. The dataset has been made publicly available through the GitHub repository. So getting into the details of the dataset, most of the songs were of a duration of from 4 to 5 seconds. We then performed a manual editing to extract 5-second clips from all songs. Apart from that, we applied zero-score normalization on each 5-second clip. Other than that, no other pre-processing was done on the clips. Thus, the chunks contain both vocal and instrumental information. Before moving on to the classification task, we need to extract the features to perform a classification. So we extracted 4 types of features. The first one is the classical MFCC features, from which we extracted a 13-dimensional feature. The next 2 features were the spectrogram and the MEL spectrogram images from the audio clips. Then we also extracted the statistical feature vectors that are mean, median, and standard deviation. So in that, for a 5-second clip, there are n frames, 30-second frames, which have a 19-dimensional feature vector, out of which we calculated the mean from all the frames, the median from all the frames, and the standard deviation from all the frames. Next up, the experiments. We conducted 5 experiments for our paper. The first one is we gave the statistical feature vector to the artificial neural networks. Along with that, we also performed the early fusion between them. Next, we represented the MFCC audio file, the MFCC signal into a image, and then gave it to a pre-trained ResNet model. Next, we the extracted 13-dimensional MFCC features were given to a convolutional net. In the fourth experiment, we gave the extracted spectrogram images to a pre-trained ResNet model. Similarly, in the fifth experiment, the given extracted MEL spectrogram images were given to the pre-trained ResNet model. Moving on to the exciting, so for the image classification, we use the ResNet 50 model because of its ability to overcome the vanishing gradient problems. And for that, we trained the model for 10 epochs for each experiment. Next, for the evaluation metrics, as in the literature survey for folk song classification, accuracy has been favored as the metric for comparison. However, due to the imbalanced nature of our dataset, in order to verify the performance, we took the help of precision, recall, and F-score in addition to accuracy to record our results. Now, moving on to the result section. As you can see from the table, for the mean, median, and standard deviation, median vector performed better than the other two. While performing the fusion between those three, we found out that there was a increase in performance, but up to a certain extent. Next, the experiment involving the spectrographic representation of audio, it did not yield significant result, as you can see here, the 67.5%, which is lower than the mean and median based classification. While on the other hand, the audio when represented as MEL spectrogram images, it boosted the accuracy to 89.7%. This concludes that this type of audio representation is promising for such tasks. Moreover, on graphing the results, we can see that the Assamese songs were the easiest to identify when compared to the Uttarakhandi song. According to us, this was the case of the imbalanced nature of the dataset. Uttarakhandi songs were about 10% of the total dataset, while the Assamese songs were around 44.1% of the total dataset. So to conclude, MEL spectrograms perform better than other features considered for the experiments. In our paper, we demonstrated a region-based folk song classification on newly proposed dataset comprising of 307 folk songs from 5 major regions of India. We compared performance of traditional classifiers using the short-term spectral features with a pre-trained ResNet based on the IFSC5 corpus. We found out that deep learning based system with MEL spectrogram audio representations outperforms all other audio representations. This indicates that there is a lot of scope in deep learning architecture to improve the existing state of art in MIR tasks. For future improvements, we plan to apply some pre-processing to the audio files, also some methods of handling the class imbalance to get a better accuracy on our dataset. To conclude, this is the link of our public repository. You can check it out. And these are the acknowledgements. So that's all from my side.
Thank you for making such a nice GitHub-based repository for the new researcher to join. But I have one question. Have you just compared? You have said that you have outperforms. How you have outperforms the previous data?
As such, there was no Indian repository that we could compare the results, but the baseline paper that we took was the Chinese folk song classification. However, the implementation methods were different, so we could not compare our results as such. But what we can see is that MEL spectrograms performed better than the other approaches that we took in our experiment.
What are the difference between the features you have observed in different, say, Maharashtra to Assamese or to Kerala? Have you got any difference, feature-wise difference? Have you observed any feature-wise difference?
We can see from the spectrogram images that there are some differences in the images, but as such, we cannot directly say there are differences by our human eye.
Actually, it is a random kind of thing, no? But it's difficult to conclude from this.
Yeah. So the main aim of the paper was to introduce a standard data set, and we performed some experiments, but in future we are planning to perform some extensive experiments to bring more light to the Indian folk song classification.
Okay, thank you. And any other question from the audience? I can see 25.
I have one, if I'm allowed to, please.
Yes, please.
Okay, yeah, thanks for the good talk. I'd like to know if you had also performed any qualitative evaluation because any kind of musicological inference out of your dataset could be very beneficial to the ethnographic community. So you are working on the audio data, I understand that, but any musical outcome is also very appreciated in MIR or computational musicology domain. So any lights on that would be appreciated. Thank you.
As such, we could not perform any qualitative analysis, but it's a nice idea. We could proceed with that in our next adventure.
Okay, thanks.
Thank you. Thanks to the speaker. Hope this will help for the others in future. So now may I invite the next speaker?
Okay, we are going to the next paper, paper ID 10, transformation of vowel duration in the speech intelligibility of children with hearing loss, writer S. Narasimhan and N. Nataraja.
Am I audible? Is my screen visible?
Yes.
Yeah. Good afternoon, one and all. I'm presenting my paper entitled Transformation of Vowel Duration in Speech Intelligibility of Children with Hearing Loss. So moving on with the introduction, vowel duration is the duration from the onset of a vowel to its offset, usually measured in terms of milliseconds. And a review of literature shows that vowel duration plays a crucial role in intelligibility of speech. Further, moving on with transformation. Transformation is referred to the manipulation of a specific either acoustic, spectral, or temporal parameter without modifying other parameters in speech. So this transformation would help us to determine the role or contribution of specific parameters in speech intelligibility. The aim of the present study was to investigate the effects of transformation of vowel duration in speech of children with hearing loss on their intelligibility and acceptability of speech. So this study was carried out under two experiments. Experiment 1 included two groups of participants. One group were participants with hearing loss and second group were normal hearing participants. The speech data was collected from both the groups of participants and it was analyzed and vowel duration was extracted. Further statistical analysis was performed to see whether there were any differences between vowel duration of participants of group 1 and group 2. Following statistical analysis, the modification of vowel duration or transformation of vowel duration was carried on in speech of participants with hearing loss to match the vowel duration that was seen in normal hearing participants. Next, under experiment 2, perceptual analysis was carried out on unaltered and transformed speech of children with hearing loss to see how speech intelligibility and speech acceptability changed. So moving on with the experiment 1, as I told, there were two groups of participants. Group 1 included children with congenital bilateral sensory neural hearing loss, and group 2 included normal hearing participants. All group 1 participants were fitted with a hearing aid appropriate to their degree of the hearing loss, and they were attending speech and language therapy since 3 years, and all the children were within the age group of 8 to 10 years. Moving on with the stimulus that was used, it was 20 bisyllabic meaningful Kannada words. These words were chosen after the familiarity testing was done by primary school teachers so that the children would be familiar with these words. Further, the data collection was carried out in a soundproof room. The participants were instructed to read the word written on the card. Normal hearing participants were instructed through auditory mode, and the hearing impaired participants were instructed through the visual mode, visual and gestural mode. So 20 words in total. The 3 times recording of each word was done using a sampling rate of 44.1 kilohertz. And the microphone was placed, the unidirectional microphone was used, and it was placed at a distance of 10 centimeters from the mouth. Data analysis included the measurement of vowel duration in speech of children with normal hearing as well as hearing loss. Further analysis of oval duration was done in the following stages. First, the file containing the digital form of the word was retrieved using Pratt software, and wideband spectrogram and waveform was displayed. Further, the oval duration, that is the duration from the onset of the oval to its offset, was analyzed. It was confirmed auditorily that only the oval under the study was selected. Thus, the oval duration of 7 ovals, that is short ovals R, E, A, U, and long ovals R, O, and A, was measured from the speech of both the groups of participants. So this figure shows the illustration of measurement of oval duration on a spectrogram. So it is from the onset of the oval to the offset of the oval. In the word Kage, the oval highlighted is A. Moving on with the results of experiment 1, as it can be seen from the table that children with hearing loss, they had a larger oval duration compared to children with normal hearing. Further, the standard deviation of all the ovals were also higher with respect to the duration of the oval compared to the children with normal hearing. And the long oval O had the highest mean, and long oval A had shown the lowest mean in children with hearing loss. However, in children with normal hearing, the long oval A showed the highest, and short oval A showed the lowest mean and standard deviation values with respect to oval duration. Further, independent sample t-test was also carried out, which showed significant differences between the subjects of group 1 and group 2 for all ovals except short ovals E, U, and long oval O. Therefore, it was concluded from the experiment 1 that children with hearing loss showed significantly longer durations of ovals compared to children with normal hearing. So thus, as a next step, we move on to the transformation of oval duration. So here, as you can see in the first figure, the oval duration shows 0.231, which is 231 milliseconds, around 231 milliseconds. And we had found that the oval duration in normal hearing speakers was somewhere around 166 milliseconds. So we displayed the hearing impaired speech, and the oval duration was extracted using the Pratt software. Further, this duration was modified using Pratt Vocal Toolkit, which is a software which can be run using, which can be started using Pratt software itself. So it is a counterpart of the, it is a part of the Pratt software where the duration was modified and copy pasted to the original sample. So in this slide, you can see 2 figures where the left one refers to the modified oval duration of participants with hearing loss, and right figure shows the unaltered or original oval duration. So now we match the oval duration in speech of children with hearing loss to the normal oval duration. Further, in experiment 2, which included perceptual analysis, we included 6 listeners, where 3 were speech language pathologists, experienced speech language pathologists, and 3 were naive listeners. And we provided them both the unaltered utterances of participants with hearing loss as well as the transformed utterances of participants with hearing loss. We asked them to rate speech intelligibility on a 3-point rating scale, where 1 indicated unintelligible, 2 indicated partially intelligible, and 3 indicated highly intelligible speech. Further, they were also asked to rate the speech acceptability, where a 0 indicated non-acceptable and 1 indicated acceptable speech. So these are the results of experiment 2. As we can see from the table and graph, the unaltered speech was judged by the raters as having 68% of speech intelligibility. However, transformed speech improved in its rating as having 86% intelligibility with improvement of 18%. Similar is true with acceptability. It was 83% for unaltered, and after transformation, we saw 9% improvement in speech intelligibility, that is 92% for the transformed speech. Thus, the results showed that listeners had reported higher intelligibility scores for oval duration transformed words compared to unaltered words. Further, the man-Whitney test was also done, which showed significant differences in intelligibility and acceptability between the transformed and unaltered words. Therefore, the results of the present study revealed that transformation of oval duration caused a significant improvement in intelligibility and acceptability of speech in children with hearing loss. Thus, to conclude, The study revealed improvements in speech intelligibility and acceptability following transformation of oval duration in speech of children with hearing loss. So the further studies can focus on effect of transformation of other temporal parameters in children with hearing loss to broaden the knowledge of on the contribution of various parameters in improving speech intelligibility. And these temporal parameters can also be targeted during speech and language therapy sessions to improve the intelligibility of speech in children with hearing loss. So these are my references.
Yeah, thank you for your nice talk. Any question? Thank you once again to the speaker
Thank
for
you.
this work for your the society. I think it will be extremely helpful for the society. Yeah.
Thank you, sir.
Thank you. Now, paper ready 21. May I ask paper ready 21?
Hello, my name is Karthik. I'm paper ID 21.
Please share your screen.
Yes, 1 second. Just let me know when you're able to see. So, I hope it's visible.
Yeah, it's visible. Yeah.
Yeah, okay. Good afternoon, everyone. My name is Karthik. I'm presenting my paper submission, which was a part of my MTech thesis. I'm from NIT Silchar. My guide was Dinesh Naik. So he's not available today for some reasons. So I'll continue without him. The title of my paper was Language Model Fine Tuning Using Second Order Optimizers. So this is the outline. This is how I'll progress. So basically, what I'm trying to present here is in the current scenario, we have first order optimizers as our go-to functions every time we need to train our model. But here we have done a study on second order optimizers, which uses double derivative instead of single derivative to train models. So I'll start with what these are. So optimizers are basically used to train our model to give a better approximation to our learnable parameters, so that in subsequent iterations we get closer to our minimum loss early as possible. So optimizers, what they do is they'll make delta changes, some delta x changes in the model parameters, and with this we'll try to predict our outcome. And if we are going in the right direction, we should see a lesser loss in each iterations. So how we have this is some literature survey. So before going to second, these are the most popular first order methods, SGD and ADAM. These both are implemented. The reason for the success of ADAM over SGD was as Adam has introduced two more terms to us, which were mean and variance. Similarly, why second order optimizers are better, because they also introduced the Hessian calculation, which I'll be explaining in the next slide. So this is how going from SGD to Adam has helped us. In SGD, you can see that whenever we start, there are a lot more number of oscillations to going when we go to our local minima. But in case of an Adam which uses momentum hyperparameter to train, we can see that the number of oscillations have reduced by a large amount. So this is how in less number of iterations we were able to get to our goal. So how momentum helps is using a similarity to rolling a ball from a mountain. We can see that as and when the height decreases for the ball, it will reach a terminal velocity. So what this will basically means is that as we are approaching our target, as we're approaching our minimum loss, we'll be going in a particular direction, and that direction is defined by where the gradient for our learnable parameters is reducing steeply, most steepest. The problem with this momentum is in next. So what we can understand is the problem of neural network training is basically called as convex optimization. So most convex optimization problems fall to the prey of called as saddle point capture. So what will happen is whenever our model is on this curve, there is no way going to a local minima, because as we can see, most of the variables will be going to a local minimum, but some will also be increasing. Some will be increasing in their value. So we cannot get to a global minimum, but will always be captured in something called as a saddle point. And there is no concrete way to get out of it. So we'll have to start retraining our model again. This is how a local minimum and maxima should look would look like. But because our model gets captured in a curve, something called as a saddle curve. So second order optimizer tries to remove this falls from a first order optimizer. So our objective for this thesis work has been broken down into 3 points. The first one was to do a case study of performing higher optimizer for our small neural networks, compare the efficiency, then to implement the optimizer for Google BERT and compare the result with the ADAM, which is the standard optimizer on which the Google BERT has been trained on. So this is one implementation of a second order optimizer called as LBFGS, limited memory BFGS. BFGS were the original writers of this algorithm. So here we can see that there's a term called minus HK, which is the Hessian calculation. So Hessian calculation is this is called the double derivative of the trainable variables in and K will K is our parameter which will tell us how many history steps are we considering for our training. We have done a study on this also. K, one result I'll be showing later. So this will help us to train our model effectively. We have done our experiments before BERT. We have tested on custom model ResNet 50, MobileNet V2. This is just to give you a rough idea how many trainable parameters each of these has. So BERT, as you can see, has a large number of trainable parameters. So it was not possible for our hardware, which had 32 cores to train it. So we had to go to fine tuning the model and prepare a study for fine tuning instead of training a complete model. So these are the data sets on which our models have been trained. BERT has been specifically trained and fine-tuned only on Square, whereas MobileNet and ResNet have been trained on Cactus dataset, which is latest dataset available on Kaggle website. MNIST has been used to train our custom model. These are the results for our custom model on MNIST dataset. Here, I have tried to show if we have multiple K values, which is multiple history levels, so 1, 2, and 3. What we can see is that if we have a higher number of steps involved in our training a second order optimizer, we'll start getting an accuracy we'll start getting a very good accuracy from beginning itself. And same is the case with loss. The only catch here is that with increasing the number of steps, we'll be requiring a huge number of memory also, because what it does is it will store the values of the trainable variable for each level and for each iteration of while we are training the model. So the RAM requirement is very high. So for a further calculation where the model size is increased too much, we have reduced our steps to only 1. Still, we are able to see good results. So this is for our custom model. Next, we have ResNet 50, and this is the accuracy graph. So what we can see is that using our ADAM, the the accuracies were going upward, but using a second order optimizer, we were in the beginning itself, we were getting very good accuracies. Although later, with increasing the number of iteration, Adam was able to catch with the with our LBFD cell. Similarly, if we see this is for mobile net, the accuracy for mobile net, here we can see a similar trend. LBFG has had an upper end when it comes for a lower number of iteration, but as we keep on increasing the iteration, Adam would also get to there. This is our experiment on BERT. So the first one is our loss graph, and the second one is our accuracy graph. So what we can see from here is that although there is an improvement when it comes to only five number of iterations, but when the number of iterations keep going, Adam is always able to catch up with LBFGs. So otherwise, if we have a limitation on our time and on our number of iterations, LBFGs second order methods have produced better results than Adam. The conclusion is from most of the examples, LBFGs reaches the peak accuracy in less number of iterations as compared to Adam. So LBFGs were favorable for small models because the difference in the accuracies which they were able to reach in a limited number of iterations was high. So so if we have models which have higher number of trainable variables, which are heavy, which are large, second order methods would not be able to work as effectively as first order methods. Third conclusion was the higher line search always leads to a faster convergence, or although the memory usage will increase effectively. So we need to manage that. So some future work that we have decided to carry on forward on. So there's always a trade-off between the hardware requirement and the time needed. So second order methods require a lot of memory, a lot of computation power, because Hessian calculation is one of the most compute intensive methods there. But the time required has to be further studied. So with better compute devices, the time can be limited. The time can be reduced. Because there has been not much study on second order optimizing, so we need to understand the strong ground, like we have most of the analysis for first order optimizer like Adam and SGD. For second order, these needs to be conducted. Third thing, what we have seen is because Hessian calculation for each layer can be done on different devices, so a distributed approach can be taken into consideration. We could not do it because we had limitation. Our college had a limitation on the hardware which was allotted to us. Third thing is because we've seen that for initial number of iteration, Adam has been able to perform a lot better than second order optimizer LBFG has been able to perform a lot better than Adam. So what we can do is we can do training on Adam and then fine tuning using SGD. That approach or fine tuning using Adam, or first order method. That in that direction also we can think of. Third, this is a timeline for our project, and these are the references which we've taken. Thank you so much. Questions, please.
Any questions from the
Karthik?
Yes, sir.
See, one thing that in your diagrams you have not given that that what is the level of the x-axis and y-axis. So it is though you have explained, you add for that in the diagram that when you have gone for the accuracy and validation and other results are there is no leveling for the x-axis and y-axis. You can see that.
This diagram, like this diagram, you see.
Yeah. No, there is no. What are the levels of x-axis and y-axis? What is x-axis and what is y-axis? Nothing is mentioned in all the results graph.
Okay. Correct, sir. Correct.
That is missing. So that means people will understand. I don't know what people will understand. You have said about something like that iteration and all this is okay.
Yes, sir.
Okay. Next point is what you said about that. Like, can you know that mention about that saddle node complexity on the given problem you have considered for that? You have tried for the second order optimization. Second order optimization. So how that that your that given current problem invites for higher level of optimization algorithms.
Okay, so in terms of complexity, the complexity has been increased to n cube. So what we can roughly say is, because in a first order optimizer we will only be calculating the gradient. So if we consider that complexity as n, so now we've increased the complexity of our model training to n cube, because first there will be Hessian calculation which will increase it to n, and then we'll have to perform an inverse of the Hessian. So an increment of n square has been done. So the total complexity of training a model has now increased to n cube.
No, that has to be there. You see, even if it is a second order also, that is what you will go for. That it is the modality means what it depends on that. Even that algorithm also has got a limitation on the level of complexity of the given problem. You understand that?
Right, sir. Right.
Do you agree that?
Right, sir. So some more analysis has
So
to be done.
it depends on the novelty. Depends on that. What is the level of complexity of the problem which is being considered.
Right.
So okay, that should have been demonstrated. Suppose mathematically, if you cannot do it qualitatively and through the results, that through analysis of not mathematical one, maybe it will be very difficult unless you understand the search space characteristic and other things there. So probably what you could have demonstrated on that means in terms of the variations of the different parameters and all that different then like how that that saddle node aspects means more number of saddle nodes is going to affect that impact that optimum results there.
Right.
Because I have seen that some of the graphs there, either later part there, the last graph is a validation graph, means what your convention of the first gradient method is performing better than your second gradient method, second order gradient method.
Right.
What is that? Yes. Why? Can you comment on that? Why the last graph you go for the yes. Last graph you saw that your second order gradient method performed poorly as compared to the first order one. Why?
Yes, sir. So this what we are predicting is it is because of the model size. So because for the BERT model, the model size was way larger than other models which we have tested. So higher order optimizer was performing poorly in case of this with respect to other models that we have trained.
No, do you want to mean that like the higher order optimization, which is supposed to be more capable in coming out with more complex optimization problems, is likely to perform poorly on lesser complex problems?
Something like that. Yes, sir. From that I can observe, but if you just see the accuracy, so accuracy is better than the ADAM in case if you just consider accuracy, not the loss. So there is an improvement, but the improvement is less in case of large or complex models, complex problems. This I agree, sir.
Okay, just think on that. Okay.
Yes, sir. Yes, sure, sir. Thank you for your feedback, sir.
Thank you, Karthik, for your nice presentation. And I think you got the idea how to improve this paper.
Right, sir. Right.
Thank you.
Thank you, sir.
So now we have to move for the next paper ID 27. No, 26, no? 26. 26. Saket.
Yeah. Can you see my screen? My screen is visible?
Yes.
Okay. So a very good afternoon to everyone. I'm Saket Agashe, and I'm a student at VJTI Mumbai. And today I'm going to talk about my paper titled Comparative Analysis of Neural Network Architectures for Speech Emotion Recognition. So I'll just set two goals before we get into this. The first is that I want to look at the recent standard neural network architectures, which have shown great results on a lot of tasks, and you see how well they perform on the task of speech emotion recognition. And the second is that I want to see if I can do it with the least, with the best computational efficiency. So before I get into that, I just want to justify why speech emotion recognition is important. So in applications like personal assistants or chatbots, which are human-computer interaction applications, it is very crucial for the devices to be able to capture the emotion of the of humans, so that they can better cater to their needs. The second application is in medtech fields, where SER automated agents can serve as diagnosis tools. They can help doctors get a better idea about the mentality and about the emotional response of patients. And the final one is that they can also be used to get a better idea about customer service, the feedback that customers leave for companies as audio files. So before we get into it, these are a few of the features that have been conventionally considered throughout the literature. There have been a lot of experiments working with MFCCs and LLDs. However, as you will see in the further slides, for our purposes, we have stuck to spectrograms as our primary features, and we also perform an analysis on the text-based models, for which the original earlier features used to be something like TF-IDF, or how frequently some words appear and not. And for that, we will see how we can use embeddings as the better feature. As far as the models and the architectures are considered, we have restricted our research to the CNNs and RNNs, because a lot of previous literature has already explored how HMMs and normal multi-layer perceptrons perform, and CNNs and RNNs have shown to give a better result. So first of all, talking about the dataset, the dataset that we considered is the IMOCAP dataset, the interactive emotional motion dyadic motion capture dataset. So the classes that we considered from this dataset were happy, sad, angry, and neutral as our emotional classes, because these were most highly represented, and of the other 8 classes that exist in the dataset, the other classes had really few samples, so it was not possible to include them in our training and testing methodologies. The next thing, which is very important, is that we implement a 5-fold cross validation. But we do it such that we train our model on 4 sessions, and we validate and test it on the final and the last session. This makes sure that the speakers and the text that the model has been trained on is not repeated in the validation and testing set, so that we can get a better idea of the generalization that a model is able to make. So now coming back to the features, as I said, so we use the MEL spectrogram features for our audio model. We also experimented with linear spectrograms, but what we found was that MEL spectrograms gave better results in all of the models that we will see next. And these were the features that these were the values of the parameters that we considered for the features. Here also we experimented with quite a few values, but decided to stick with these as these gave the best results. The next thing is about the text features. Here we obviously use the word embeddings, which are almost ubiquitous nowadays. They are used everywhere. What we did was we trained using the randomly initialized embeddings as well as using pre-trained glove embeddings. And as we'll see further, we can see how that affects the models. So now getting into the models, first we'll look at the audio models. But before I get started, I would like to bring all of your attention to the actual spectrograms. As you can see, there are clear spatial visual characteristics in these audiograms which correspond to the 4 classes. And it is not just for this image, but throughout the data set, a lot of these spectrograms do. So a lot of angry spectrograms are similar in their visual spatial characteristics. And we will try to use our CNNs and GRU models to try to see if they can represent this data well. So the first model that we are going to consider is the convolutional neural network. So this is the image of our model, and the features and everything is mentioned in detail in the paper as well. But the one thing that I would like to bring your attention to is we are not using any max pooling layers, but rather going with 2x2 convolutions to downsample the data. This decision was taken because in a paper published in 2019, the researchers found out that using such stride convolutions to downsample the data performed really well. And so we decided to try it out in our model as well and see how that performs. the final layer of the CNNs are flattened to feed into the linear layers, and then the output is softmaxed to give the 4 classes. So this is about the CNN architecture. The next architecture that we'll look at is the GRU, or the gated recurrent unit. Here also, since spectrograms are basically 2D features, which are very similar, like in their dimension to embeddings, we can use the spectrograms as features to gated recurrent units, which also expect a 2D input. So where the time axis of the spectrogram acts as sequential data, while the frequency information are the features. Now we used a 2-layer GRU, and we used a bidirectional GRU, and the output of the GRU is then passed on to a fully connected layer and then softmax. The next interesting thing that we did was we combined the CNNs and the GRUs. Here you have to do it quite carefully, because you can't just flatten the output of the CNNs and pass it to the GRUs, because that has no sequential information. So what you have to do is preserve the time axis information and then stack the frequency and the filter information as the features, and then pass this data, these features to the GRU network, and then the GRU itself passes the data to the fully connected, and the output is softmax. As you can see, all of these models are relatively shallow. They are not very deep, and so they are computationally quite efficient, which is important to us, because we also discussed in the start that we want to make sure that we can use such models in personal assistants or other edge devices as well, and computational efficiency is quite important there. Now taking a look at text models. So here we considered only two of these models. We used a bidirectional GRU and a bidirectional LSTM, and we coupled it with the attention mechanism, which has shown better results in all of our literature survey, and it is quite intuitive as well, because the attention layer basically helps to pinpoint the right words and right phrases inside the sequential data, so that a better classification of the emotional response can be made. So this is the bidirectional GRU model. As you can see on the right, we have the input embeddings, which are fed to the GRU model, and the GRU itself is passed on to a linear attention layer, and then the output is softmax. The LSTM architecture is also very similar to the GRU architecture, the only difference being that we are using LSTM units here. So now the evaluation criteria. So what we did here was we used weighted and unweighted accuracies as our primary evaluation criteria. So weighted accuracy is basically considers how many instances of the class there are. So it is the number of correctly predicted instances in that class divided by the total number of classes and then averaged over all the classes. Whereas unweighted accuracy is just your average accuracy, your normal accuracy score, which basically takes the total predictions and divides by the total number of instances in that samples. So here we see that if you can first focus on the audio models, the CNN and the CNN GRU stacked model both perform quite similarly. They don't really have a lot of difference in their accuracy scores. However, both of them perform significantly better than the GRU model in both of the weighted as well as unweighted accuracy. And looking at just the unweighted accuracy can be slightly misleading, as I'll point out in the next slide. So considering both the accuracies is quite important in this context as well. So as far as the text models are concerned, we didn't really find a large enough difference in either of those. So both of those models perform quite well on the sample. The thing that I would like to note here is that all of these models are significantly shallow models. They have only 4 CNN layers or 2 GRU layers, and a lot of the conventional models or the new models that are very deep have a lot more computational complexity than these models do. They have the conclusions that I would like to draw from these are first of all that as we saw on the previous slide, that the CNN model here outperformed the GRU model when we use the spectrograms as the features. The second and important thing is that the IMOCAP dataset has a significant class imbalance in that the neutral class is overrepresented, and therefore, if you just train the model as it is, the model almost always overfits to the neutral class. Therefore, it is important to take a weighted sampling or a weighted loss function that makes sure that this sort of problem is avoided. And the final thing is that we saw that the embeddings that we had randomly initialized were actually performing better than using pre-trained glove embeddings. However, I believe that this is a consequence of the particular data set and its size, and that as the data set size gets bigger and the model is more generalized, the glove embeddings would also perform very well. Moving on to the future work, I think that first of all, we need to consider more number of architectures, like the transformer architectures, which are beating the conventional sequential models at almost all the tasks in the current research. And we think that we can use the transformer architectures to get better output from audio and text data. And the important thing here is that not the entire transformer architecture, but the distilled and pruned versions of the transformer architecture have actually good computational efficiency. So I think that is something that we want to try. The second is multimodal analysis of the IMOCAP dataset itself has shown better results than just considering speech and audio data. The speech and text data. And we believe that we should focus on building a system that basically takes in a speech input, converts it into its text representation, and then that entire thing is fed to a multimodal sort of system. And then training the model based on such a system is a good future research point of view. And the last, and I guess the most important one, is that since the audio, at least the audio system is language agnostic, we want to consider something like training the models on the, let's say, the IMOCAP dataset, and then fine-tuning it on smaller Indian language corpuses and seeing how much such kind of transfer learning is helpful in this context. And yeah, that's all for us. Thank you. And
you mentioned that you will include in edge devices, right?
We have not performed any computation on edge devices. We are just saying that we need to consider edge devices as well when we build large enough models.
But how you'll perform this convolutional neural network in edge devices? It will take a lot of space and energy. And
yeah. So, but if the model is small enough, it performs okay enough on a CPU. So let's say your mobile phone or something like that. There have been a lot of progressive web apps and such that have basically directly not trained the model, but has inferred from the model on the mobile device. So that's what we want to be aiming for. Not training it on the edge device, but rather inferring the output on the edge device.
Okay. So any question from the audience?
Saki.
Yeah.
See, can you tell me that looking into your problem, how and why? What is the novelty of using that LSTM for textual part and CNN and other part GRU for audio part?
Yeah. Okay. Yeah. That is a good question.
You know that what are the places or what are the situations where this type of networks are supposed to perform promisingly?
Yes,
what are the situations? What are the type of problems?
Basically, when there are visual and spatial features, the CNN is usually supposed to perform better.
No, I don't know. I don't think that. See, that is what there is some I don't know what I should say. You see, specifically, you talk about that. That you are just take the case of the textual part is there. That when you go for that emotion and other that sentiment and other thing is there. Do you want to mean that over the temporal variations, the sentiment varies?
No, it doesn't vary over temporally. It doesn't vary temporally.
No, you see that why LSTM is considered?
So basically, LSTMs are considered because they have a state which can basically map out the entire sequence. So if I say something like
yes, means
good
what
boy,
sequence means, that sequence is temporal. That sequence is very much important for that. When you have the sequence, so that sense means what audio part is so much more relevant for the application of the LSTM part, because that the signal when you have that one is there. So sequence is very much important. That case you go for that LSTM part. But you just consider about some text are there, individual text, this text, that text there. In that case, unless you have combination of 2 or 3 words there, there is wide variations of that type of that expression of the sentiment by using words.
Yeah.
So can you just that you said about that? Okay, the general talking about that is there. CNN is there. CNN you have applied for that is there. Their performance is what CNN plus GRU has not improved much. Why? Do you have any idea?
I think that
because first thing is what CNN you are using with a perspective or with an objective, and which may have some limitations, and which you want to overcome with the use of GRU. If you feel like that, that is what. Can you tell about that?
So I
what
think
are the limitations of CNN which is compensated by GRU?
I think that so the GRU is a better representative of, as we mentioned before, the sequential data, which I think that a GRU can do much better than a CNN, because the CNN considers a smaller spatial area at a single time, whereas a GRU can have a state that maps to the entire sequence, which is also relevant in the case of audio, because in spectrogram features there is a time axis and a frequency information axis. So over the period.
But CNN is having more of that, that when you go for that localized filtering aspects and these things there, it has got, and I don't know that you should have compared with some other already reported one. Then only you would have that which are used for that specifically speech or audio signal processing or something like that. Then probably you would have got much more insight into that. Means what you wanted to do something. Because this whatever results you have shown is what is the CNN and with GRU of that one you have compared with that.
Yeah.
That should have been more relevant would have been there. What are the methods or neural network which are already used on that audio signal processing there? With that means also they improvised on that with that your concept, then that would have been much more informative. That have been.
Okay.
You can think of that part is there even because LSTM even you should have also tried for the LSTM with that also.
So here we did try LSTM and the GRUs were slightly better than the LSTM. So since I wanted to compare it between the CNN and the recurrent network, I stuck with the GRU.
No, this is my point is you have already proposed these two things there. That has to be, there must be some novelty in consideration when it's just like that CNN is what everybody thinks about the deep learning. So it is going to be deeper. You have to have some premise of that why one should go for deeper. Again, you after going deeper one, you find out that it has got limitation. You are not getting what is expected. That is why you are looking for the GRU. My point is that. That could have been, demonstrated in a better way, like coming out with that already reported one, and why you require for going for the deeper one, and again going to the deeper one, you require some sort of limitation. You come a piece of that one is there that urged you to that made you to feel an urge to go for the GRU. That could have been demonstrated in better way, coming out the same way the results of that one.
Okay. Yes.
Thank you, sir, for your constructive comments. I think it will be extremely helpful for the speaker. I think for the future upgradation and improvement of these projects. Now, thank you.
Okay, I have one request. May I request? Hello.
Yes.
Okay. May I request all the participants and shares while speaking, please turn on your video. So everyone is not looking in the scene, so it's not looking good. So if possible, please turn on your video while speaking. And I can understand about the internet issues. So it will be better if you turn on your video. Okay, thank you. You can go for next paper.
27. Paper ready 27.
So is my voice audible?
Are you present?
So is my voice audible?
Yes, yes.
Okay, sir. So I'm hoping my presentation slides is also visible.
No.
So my slides are not visible yet.
So you share your slide. You click the share button.
Yes, sir.
Yeah.
Sir, is it visible now?
Not.
Yeah, it is coming. Coming. Slowly it is coming. Yeah. Yes, yes. Visible.
Okay, sir. I will.
Please start. Please start.
So very good afternoon, everyone. My name is Thangjam Kleinda Devi, and I'm a research scholar at Indian Institute of Information Technology, Senapati from Manipur. So today's topic, my paper title is Vowel-Based Acoustic and Prosodic Study of 3 Manipuri Dialects. Paper ID is 27. Um, so this is the outline of my presentation. So I'll just briefly go through the introduction, and then since this is a study of 3 dialects, so what is the data set I have used in my study? So I will discuss about that. Then I'll go to feature extraction. What are the features that have been extracted? And we'll discuss the preliminary analysis of the features extracted, the results, and then I'll finally conclude and also talk about the future scope of this paper. So the introduction, dialects of a language are identified by the unique speaking patterns followed by the community of speakers belonging to a particular geographical region. And it is believed that dialect information is present in a speech signal, which contains both at the segmental and suprasegmental level. And there are no previous attempts have been made. No previous work are there in related to vowel-based acoustic and prosodic study of Manipuri dialects. So since this was not available, the experimental study, so this was the motivation for my work. So those of you maybe may not know, so I'll just briefly talk also about what is about a Manipuri language. So Manipuri language is a Tibeto-Burman subgroup of Sino-Tibetan language family. So it is the official language of the state of Manipur, and Manipur is in the northeastern region of India. So it has basically many dialects, which is such as Imphal, Andhro, Sekmai, Kapching, Kurkul, Thanga, Kwatha, Phaying, etc. But in my study, I have only considered 3 dialects, which are Imphal, Sekmai, and Kapching. So the data set that I have used for this study is basically I have got this data set from Linguistic Data Consortium for Indian Languages. So I requested for Manipuri speech corpora from there, but it was a huge data, so I have only worked on the subset of this. So the reason also I will discuss about it. So basically I have taken, so I have only considered they had some folders, so they have some stories and some paragraphs and different names and places. So all the words lists are also there, but I have considered some sentences which consist of words where phonemes can occur in various positions and are meant to show the dialectal variance of the speakers. So I have worked on only the sentences part of their speech corpora. And again, so their data set contains speech files from 150 speakers, and each speaker has uttered 25 randomly selected sentences out of 208 unique sentences, and age of speakers varied from 16 to 51 years. So since this is a vowel-based study, so the sentence level annotation, so they have also sent me the text transcription of the speech utterances, but I was working in the vowel-based, so I had to do the annotation at phoneme level as well. So this was done manually by using Pratt's Speech Analyzer toolkit. So I have done the vowel annotation there. So since the annotation takes a lot of, it is a time consuming process, so I have only worked on a subset of data. So this is the vowel frequency distribution table. So in their data set, only 3 dialects data was there, so which is Imphal, Kutchi and Sekmai. So totally I have considered 1080 vowels uttered by 45 different speakers. So almost equal distribution of gender in each dialect has been taken into consideration. So the total number of vowels for Imphal, Kutchi and Sekmai is 320, 370 and 390 respectively. So number of speakers considered is 7 for male in the Imphal dialect, 7 male, 8 female, 8 male, and then 7 female, 7 male, and 8 female for Sekmai dialect. So this was the again frequency distribution table. So I have considered 6 vowels, so which is a, e, o, u, a. So 6 vowels I've considered, which are common to all the 3 dialects of Imphal, Kutchi and Sekmai. So this is the percentage of occurrence showing in a particular dialect what is the percentage of occurrence of every vowel in the dialect, in each dialect. So let me start with the feature extraction part. So for segmental, at segmental level, the formant frequencies have been extracted, and at suprasegmental level, the segment duration, energy values, and pitch contour values have been analyzed. So formant analysis, this figure is showing the traditional F1, F2 plot. So this plot shows the vowels in the order. So here we can see, so the red colored is for Imphal, and blue is for Kutchi, and green is for Sekmai. So this is the traditional plot. So from the figure we can see that the vowel space, so as I've said, I've only considered the 6 vowels. So for these 6 vowels, for Imphal dialect, we can see that the vowel space is a bit larger compared to the other 2 dialects. And then the front vowels, E and A of Imphal dialect, have higher F2 values than the other 2 dialects. So significant differences can be seen in the 3 dialects according to the data set which I have used. So since this is a preliminary analysis, so there was no work in Manipuri language, so I just started the work like that. So also this features extraction part is also done using the Pratt toolkit. Next is segment duration. So it is also believed that dialects can be distinguished based on segment length as well. So this is the duration of the segment it corresponds to the perceptual property like speaking rate of speakers from the 3 different dialects. So here also we can see some significant changes in the 3 dialects while pronouncing the 6 vowels. So here we can see the vowel duration in seconds, the y-axis. The x-axis shows the different vowels considered in my study. Next, I've also extracted the energy values. So the energy values is also has been extracted using the Pratt toolkit. So short time energy has been computed from vowel sounds for describing the loudness. So this is a perceptual property is loudness, which corresponds to the energy. And energy variations with time are measured concerning samples amplitude within a frame. So statistical information, namely mean, median, max, mean, upper and lower quartiles have been analyzed. So in this figure, we can see that this in the boxes actually. So the horizontal lines of the rectangle, so as you can see, there are 3 rectangles for each dialect. So the horizontal lines corresponds to the lower, median, and upper quartiles respectively. So the values have been extracted, and then those values have been plotted. This is a box plot. So energy values have been shown using this box plot. So this small letter O and then star asterisk. So all these are outliers. So there are some outliers also present in the energy values extracted. So this is showing those outlier values, and the horizontal line, the dark line inside the box shows the median, and also we can see one dotted line inside the box. So this dotted line is showing the mean value. So once we get the energy values, the mean value is shown using this dotted line inside the box. And this whole box, the first horizontal line is the lower quartile, then the median value, then the upper quartile. So next is the pitch analysis. So they're also by using autocorrelation method in Pratt toolkit. So the F0 values were extracted from the speech utterances, and this is the average F0 values in hertz shown here for different vowels in each different dialects. So here also we can see some differences, but definitely we use the pitch analysis for either intonation or tones. And this Manipuri language is a tonal language. It has basically 2 tones, high tone and low tone. So I have not included the tonal part in this study because I just started with this. So my future work, I'll have to include the tonal. So I might have to annotate the speech utterances. So if I annotate the tones as well, the high and low part, I think I might get some better results. So a more cross-dialectal study for tones is required. But this is also showing some comparative gender dependence. So using the same F0 values, the average F0 values for male and female. So this also I'm showing by using the plot. Conclusion is this study has reported the vowel-based acoustic and prosodic analysis of 3 Manipuri dialects after the creation of vowel dialect dataset. So from the available Manipuri speech corpora, I have created the vowel dialect dataset, subset of those speech corpora after doing the annotation at phoneme level. So after annotating all the vowels, all the 6 vowels in the speech files, so I have tried to analyze the vowel-based approach. Then initial analysis shows a difference in the vowel spaces of the 3 dialects according to the data set which I have considered. So there we can see some differences in both all the features, so at segmental and suprasegmental level. So this gives preliminary results, and obviously some more in-depth cross-dialectal study is required. And for future scope, this after properly extracting the features, obviously these features can be used in the application of automatic dialect identification. So where it will classify which, after we give any speech utterance as an input, it can identify which dialect category it belongs to for Manipuri language. So that is my future work, planning to do that. And also extending the size of the data set, basically. So these are my references. And thank you. So any suggestions and questions are most welcome.
Yeah. What software you're using, Mr.?
Sir, Pratt Toolkit.
Okay. Is it freely available?
Yes, sir.
So there is something Python based. Have you tried with Python based some modeling?
So for classification purpose or for feature extraction?
Both.
Sir, you're asking about the feature extraction part, or sir, the classification part?
You know that both can be done. You know that there's some Python tools where you can have the more flexibility than the tools only you have used. I think you can try. There are some things available already in GitHub.
Yes, so I'm going through that to use Python. Also, I'll be using Python for, if I have to go for classification method, then anyway I have to go for learning Python. So there, what are the feature extraction methods I have to consider, sir?
So any other question from the audience?
Anjam,
yes.
you have you have got that F1 score and F score and all these things. So this one for all the 5 vowels, see about that level. So how did you go for that? Did you go for that across the different dialects? Means what? Is it related to that one, the dialect related to a particular event or particular that description of same thing across the different dialects? How did you collect that? How did you get the informations about that?
Sir, the F1 and F2 values?
F1 and F2 values, how did you get across the dialects? Because you have compared across the dialects across the different regions, no? How did you get that? How did you get that?
Sir, while performing the annotation, so...
No, annotation means what? You see, they will be speaking about something, no?
Yes,
when they're speaking about that, they will be using some language there, some dialect will be there. So it means what, to describe something. So is it the same event which is made to be, that expressed by this people and this region people, that region people and other region? Is it like that, or you have gone for different, events and different descriptions?
Sir, there are some common sentences uttered by all the speakers in every dialect, but I will not say that my data set contains equal, like the same sentences uttered by the different speakers. It is not like that, but I have tried that most of the sentences should be common in all the 3 dialects. So like that, I have taken
then
the
you see,
sentences.
there will be no. My point is, there will be thousands running up to that. Even that few thousands of thousands sentences will be there. That one, the words will be there. So my question is, what when you go for that? This is a statistical data only. This is F1 score, F2 values are statistical values. So these values will be relevant. You will be drawing the inferences based on these values. So if the values itself is collection itself is, it means what you want to, you expect that these values will convey some informations about the similarity, dissimilarity. I feel, is it not? Yes. So in the premise is not same, then how can you draw similarity? There will be utter mistake in that, inferences. It will never be same. The premise has to be kept same for all the dialects across that, and then go for do experimentation. Then it will be perfect, scientific, more scientific. Because you have just gone for this region people, and with some you have taken some sentences, and that people some other sentences, that people some other sentences. No, it should not be. I don't know, because what you follow, things your procedure you have followed. If that had been there, then it will be, there will be real scientific mistakes there in conduct of that experimentation, and it will definitely give the wrong inference. You understand my point, my perspectives? You see, you make this region people to describe about something, to state about something, which is, so other region people also same thing there in their dialect, and another region people same thing in their dialect. Then only it will be much more relevant. Otherwise, it is meaningless. It is misleading.
Yes, sir. My doubt is, sir, majority
people,
of
how
the...
do you go for that in there? I do not know your procedure or something like that, but this is my common sense tells about that.
So most of the sentences are common in all the dialects.
No, that is what, like I say about that. How do you say the most sense? Common with that may be there. My point is what the premise should be, same. That is what my point.
Yes.
Premise should be same. That is the point. You don't understand that. I think that how much important that issue is there, aspect is there. Otherwise, it is something like, somebody will be describing a football, another one will be describing the cricket, somebody else will be describing about the patient description. Then it is never same. A lot of difference will be there. No way you can draw similarity and dissimilarity methods. Anyway, just look into that. Okay, this is my concern. I'm just saying about that. I don't know about that. Your all the whole methods and other procedures and all this.
Thank you, sir, for
Sir,
your
I will-
advice. And now, thanks to the speaker, I think you got a lot of information and constructive suggestion from sir. From
yes, sir.
NIT Silchar, sir. And now I'm going to the next speaker, paper ID 30, Rubel Dash. Thank you. Rubel Dash is present. Rubel Dash is present. Paper ID 30.
No, he is not present, I think. I can go for next one. Meanwhile, I'll contact.
Yeah. Paper ID 41. Who first? Paper ID 41.
Yes, sir. I'm there.
Yes, yes. Please start your presentation.
Yes, sir. Is my screen visible?
Yes, yes.
Yes. Yeah. Yes.
So you're giving presentation from Canada?
Yes, sir. Yes, sir.
Okay. So what is the time there?
It's morning, 8 o'clock.
Okay. Thank you for joining.
Not a problem, sir. Hi, I'm Sri Harsha. I'm working with Jason and Dr. Sagil Ud of Dalhousie University and Victoria Institute of Canada. Today, I will be presenting my work on sine wave speech as pre-processing for downstream tasks. So the outline of this presentation is I will be initially giving a small brief introduction about speech production, then about the sine waves-based representation of speech.
Chirasha, please turn on your video if possible.
Oh, yes, sir. Sure. Yes, I'm visible now?
Not yet.
I have turned on my video.
Okay, if there is any issue, you can go ahead.
Yes, yes. So I'll be. Sorry.
You can go to that.
Is the screen visible?
You can go to this full screen, that one, then go for video, I think. You have to come out from here, go for full screen, that one share, and then go for video, playing the video. I think that may work.
I have tried, but it's not working.
Stop sharing the slides and go for the full screen share, then go play the video.
Okay. Yes.
Yes.
All presenters, please, you too also turn on your video while speaking.
Now am I visible, sir?
Yes, you are.
Yes. Okay. So this is a perceptual analysis completely based on perceptual analysis of the sine wave speech for emotion recognition. And finally, I will be presenting a summary and the future work of this work. So coming to the introduction, speech, as we know, is a time-varying signal which is produced by a time-varying vocal tract system excited by a time-varying excitation. So having a time-varying vocal tract system and a time-varying excitation, speech is a highly variable signal, which is assumed to be quasi-stationary in very short durations. And having such a highly time variable, speech is very complex. And if we see the time frequency representation of speech or the spectrogram, we can see that at any instant of time, the energy is distributed across a vast number of frequencies. But in the spectrogram, we can see that there are specific frequencies where most of the energy is concentrated. These patches or these frequencies are called the resonant frequencies or the formant frequencies. And having said, speech is a complex signal, and having its energy spread across multiple frequencies, and also most of the energy is concentrated across specific frequencies. Speech being so complex, it's highly computationally expensive. So can we just consider these formant frequencies to get a representation of speech, which is computationally less expensive and easy to be accessible? So one such approach is to use sine wave speech. So as per Fourier analysis, we know that speech can be represented, or any complex signal can be represented as a sum of sine waves. And speech also can be represented as a sum of sine waves, where we need to have very infinite number of sine waves to represent the speech. But instead of having such large number of sine waves, can we consider only a few, maybe 2 or 3 sine waves to represent the information in speech? And these sine waves, in our case, will track the formant frequencies of the speech signal. So we consider the first 2 or 3 formats, and we generate sine waves which have time varying frequency, which track the formant frequencies, and then we add these sine waves to generate a simplified representation of speech. So as we can see in the spectrograms, there's speech signal, which is the first one, and the second one is a spectrogram. The energy is distributed across multiple frequencies. Whereas in the sine wave speech, which is obtained by considering only the first 3 formats, there are only 3 formats, the energy is distributed across only 3 frequencies. So having such a simplified representation of speech, does it carry any information? So there are some previous studies which analyzed how the simplified representation of speech, what information does it carry? So there were some studies on linguistic content, which shows that the subjects or the listeners were unable to grasp the information just from the simplified representation of speech. But when they had a prior knowledge about the speech, they are going like the speech, and then they were presented with the sine wave, they were able to relate the sine wave based representation to the speech. This means humans were not still completely trained to understand a sine wave based representation of speech. And more interestingly, some speakers, some listeners were also able to perceive this sine wave representation as a music. And this could be a consider for future work of converting speech to music. And later, there were some studies which conducted on speaker-based information, like can we recognize the speaker just from the sine wave representation of speech? And interestingly, the listeners were able to recognize the speaker from the sine wave based representation of speech. So in this study, we were interested in finding like whether speakers can recognize the emotion of the speech just from the sine wave based representation of speech. So here we are doing only a perceptual evaluation to see how listeners can perceive the emotion that is captured by the sine wave based representation of speech. So in our study, we extract the sine wave based representation of speech by first computing the magnitude spectrogram of the speech signal, which is the short-term magnitude spectrum, and then we compute the first three format frequencies, and the instantaneous amplitudes in the magnitude spectrum around the format frequencies is considered as the amplitude of the formats. And further, we do a voiced, unvoiced decision on each frame because the extraction of format frequencies is not reliable in the unvoiced regions. We just consider only the voiced regions and we discard the unvoiced frames. And now we have a format frequency for each frame. Now we generate a sine wave, which time varying frequencies, which is track the format frequency. And we just sum up these sine waves to generate a simplified representation of the speech signal. And for this analysis, we are doing a perceptual analysis. We are considering a data set, which is the database of emotional voices. It has parallel sentences, like the same speaker utter a same sentence with different emotive states. And here the three different emotive states are amusement, anger, and sleepiness. And we are considering different utterances. And moreover, for the sine wave-based representation of speech, we are considering three different cases where we consider the first format, where we consider the third format, and we consider the sum of sine waves extracted for first, second, and third format. So it's like sine F1 is the sine wave which is extracted using only the first format, and sine F3 is the sine wave generated using the third format, and sine F1, F2, F3 is the sine wave which is generated by adding the sine waves of first format, second, and third formats. And the perceptual evaluation was done by asking 14 subjects to give a label based on what the emotion they perceive when they listen to the sine wave. And these subjects has no prior knowledge about the linguistic content of the speech. And in order to avoid any bias, the sentences were provided in a very random order so that the subjects might not get biased to the order in which the sentences are being presented. And if we see at the results, it's quite interesting that just using only the sine F1, which is the first format, the subjects were able to recognize speech up to 1/3 of the times they were right. But if we go to the third format, again, 1/3 of the times they were right. But if we have a first three formats, the sine wave-based representation of speech, they were able to perceive 65% of the times what emotion it is. And of course, this shows that the sine wave-based representation of speech do carry some emotion-specific information. One way why some speakers might have failed is they might, like we humans are not well trained to perceive emotions from representations other than speech. That could be one option, or the other thing could be like still more information is needed for humans to perceive emotion from speech. And coming to the summary and conclusions, so first, just considering only a single format might not be sufficient for humans to perceive the emotion from speech. We need more than three formats to extract the emotion-specific information from the speech. And second one is that just the format frequencies will carry the emotion-specific information. And as a future work, this is just a perceptual and evaluation, but we also are trying to see how machine learning models can be used to classify speech just using the sine wave-based representation. And why this is important? Because, as I have mentioned earlier, speakers were unable to extract or grasp the linguistic information in the sine wave-based representation of speech. So this could be used for anonymization, like when I have to do a downstream task like speaker recognition or emotion classification, I don't need to have the entire speech signal, but a simplified representation of speech, which might not convey most of the linguistic information, but still can be used for classification of the downstream tasks. And when speakers were asked to perform the emotion classification just using the natural speech, they were able to go up to 75 to 80%. So there is not much variation from these two domains. So this could be one more thing. And the other thing is, in this study, we have considered only the format frequencies, but we haven't considered the F0, which represents the excitation source information. So that could be one interesting way to look how can we extend this work. And finally, this could be used for anonymizing speech, which we are trying to do for some depression analysis. And that's the end of my presentation. And any queries, please?
So what kind of machine learning things you are planning? What
So we are trying to look at emotion classification and depression classification. Depression analysis is one more task I'm working on. Like, can we, because generally the issue with depression analysis is people are scared to share their personal opinions. Like in depression analysis and in depression questionnaire, generally people has to share their personal experiences. But sharing such experiences could, like people are not, well, like they're not quite confident to share their personal experiences, and which can go online and people might look. So we are trying to anonymize those recordings and use them for emotion and depression analysis.
Okay. Yes.
Yes, sir. Good morning.
Yes, sir. Good morning, sir.
I think it is really, enlightening means what I see, that it is a new way of transformation, transforming that
Yes,
audio signal. No, you have used it for audio signal. Can be used for some other also similar type of, random variations, random signals or something like that is there? Time varying signal or something like that.
We also tried for music. Actually, as I have mentioned earlier, some speakers were able to recognize this as music, like perceive this as music. So we were also interested in, like, can we convert speech to music?
Yes.
So
But as you said about that, that as you said about that intelligibility, that will be a limiting factor. That will be a very much limiting factor in the music part. I'm just okay. If you go for music, suppose you have a music there, which is a combination of, you have that flute, then drums and guitars and other like that. It is very that because of across that instruments, there will be a lot of similar spectral features will be there. Anyway, my point is, this is what from the classification of or identification of the speaker or classification part, it may prove to be very effective one. It will be there. And I don't know about that emotion, as you said about that, is there because you are counting more stress on that, voice of the person, voice of the person. So of course, what that changes in that, voice because of that emotional, state of the person concerned. So that I don't know, that has to be okay. That may be also, at what level, I don't know that, because we have whether you have got any experimental results on that or not. But this is a nice way of presenting that everybody is looking very much that eager to know that at least what some sort of that this is another way of what transformation of the signal, audio signal, in some other domain, some other form, some other form, which is comparatively should be simpler from the classification task point of view.
Yes,
of course, that may be
like,
there. Okay, this is what.
Yes, not just classification, but we were trying to do some kind of a domain transfer using cycle GANs, and the issue with that is speech being a complex signal, reconstructing back the spectrogram from other domains is very tough. Whereas if you have such a simplified representation, converting from another domain to this kind of simplified representation is much easier to train networks, like such complex
that
networks
is what
like
I'm telling.
cycle GANs.
Because that whatever you have proposed for that sine presentation is what, and of course I don't think that what is the spectrum limit of that, or spectrum size of this in your new format.
So like we are just considering the.
When we talk about that, suppose you go for the spectrum also, that itself is about combination of thousands of sinusoidal signals on. spectrum is nothing but it is a combination of thousands of sinusoidal signals. Whereas the complex one you just go for transformation is basically nothing but it is what is a that Fourier transform and that type of that is basically is a spectral of thousands of signals, so sinusoidal signals, all are sinusoidal signals, presumed to be sinusoidal signals. So you have come up with a simplified way of that because I have seen that the method you have used for that conversion from that that spectrum, then spectrum from there you wanted to extract that variations in the spectrum, and from the variation you wanted to get that one some sort of sinusoidal variation from there, getting a sinusoidal variation of that type of signal you wanted to capture for that. And that is a nice idea for that one is there. Till now I haven't seen anyone coming up with that type of idea. It's okay.
Thank you, sir. Thank you for your constructive criticism, and I believe that it will be inspiring for all of us. And for the shortage of time, I cannot take much questions. So we have to go paper before the validity session starts. So we are going.
I will be happy to even contact you back on online or some other thing if anyone has any questions. Thank you.
You can contact the through online.
Yes, sir.
47 paper.
Thank you very
Thank
much.
you very much. Thank you.
Thank you for your time.
Thank you. Paper ID 47, Bhumika. Paper ID 47.
Yes, sir.
So you just directly go to your contribution part because we have only shortage of time. So you can start your presentation. Try to cover by 7 minutes, 7-8 minutes. Okay.
Hello.
Hello. I think the previous speaker has not stopped the thing, right?
Srihasha, please stop sharing.
Please stop sharing. Yes, yes.
Is visible?
Now you.
Hello.
Now, Bhumika, you start. Start the presentation. You can take the help, no problem. There is a share button on the screen. You can
Present now option is there.
Present now, yeah. F5, F5.
Good evening, everyone. Myself, Bhumika, student of Audiology and Speech Language Pathology from All India Institute of Speech and Hearing, Mysore. Today, I'm going to describe you the effects of musical training on auditory spatial processing abilities, which is a psychoacoustical and perceptual study. What is auditory spatial processing? It is nothing but detecting and monitoring different sounds in three-dimensional space. Sound is analyzed using
time, level, and frequency dimensions. In a similar way, auditory spatial processing is analyzed using interaural time difference (ITD), interaural level difference (ILD), and frequency-wise virtual auditory space identification (VASI). There are numerous studies that evaluates the benefits of musical training on temporal and other auditory acuity measures, whereas there are very less research on effects of musical training on spatial acuity. The aim of the study is to quantify the influence of musical training on closed field spatial acuity. The primary objective of the study is to study the effect of musical training on spatial acuity in isolation, that is ITD, and ILD in combination, that is VASI, and perceptual outcomes, that is spatial SSQ. The secondary objective of the study is to analyze the spatial error patterns between the musicians and non-musicians. There were 30 participants taken into the study. The study has been divided into two groups, Group 1 and Group 2. Group 1 consists of participants who are instrumental musicians, and the non-group 2 had participants who had no formal training. Each group consisted of 15 in number, and the age range considered for the study is 18 to 30 years. All the participants were ensured to have normal hearing sensitivity with no associated problems. There were no otological history reported, and otoscopy and tympanometry was performed at the beginning of the study, and then a battery of ITD, ILD, VASI, and subjective assessment SSQ was administered to all the participants. Moving on to the closed field battery test, that is interaural time difference. There were 3 white noise bursts was presented in each run at an intensity level of 65 dB SPL using MATLAB. 3 down 1 up transform staircase procedure was used. A 3-interval force choice method was used to arrive at the ITD thresholds. The participants were instructed to indicate the variable stimulus. As you can see in this slide, there are 2 standard stimulus and 1 variable stimulus. The participant is instructed to indicate this variable stimulus, which is more lateralized towards the right ear, that has a time lag. And the outcome was an average of last 4 reversals. Moving on to the interaural level difference, which is a second closed field test. The instrumentation and stimuli were similar to that of the ITD threshold, except the stimuli in varied stimulus were louder in the right ear. The participants were instructed to indicate the louder stimulus, which is lateralized towards the right ear. As you can see in this stimulus, the participant had to identify this stimulus. And the third closed field test, that is virtual auditory space identification, VASI. The stimuli were created by convolving 250 milliseconds wideband noise with HRTF using SoundLab. There were 8 spatial perceptions in 8 different directions, as you can see in this picture. The stimulus were presented at an intensity level of 65 dB SPL using Paradigm software, and the stimulus was played randomly at 8 different locations, 10 times in each location, collectively of 80 stimulus. And the participants were instructed to listen to the stimulus and asked to respond by clicking on this dummy head, at which angle the person perceived the sound. In addition to closed field tests, a subjective ratings of spatial acuity, which is a SSQ, was administered to all the participants. This is an Indian version, which is a questionnaire with 14 questions. The participants were instructed to rate it from 0 to 10 according to the localization ability that the participant can perform the task. Statistical analysis was done where the data was subjected to normality test, that is Shapiro-Wilks test. MANOVA was carried out to determine overall result of the overall result of the study, and additionally confusion matrix was done to analyze the auditory spatial errors. This is the results of Shapiro-Wilks test that reveals that all the data in the both the groups follows the normal distribution. This is for ITD and ILD, whereas this follows the normal distribution for VASI and spatial SSQ. MANOVA test was performed and it indicated that all the four tests were superior in musicians compared to that of non-musicians, and the mean and standard deviation were calculated. This is for ITD. The blue lines indicates for musicians, and the red dots indicates for non-musicians. This is for VASI. Musicians scored lower thresholds in ITD and ILD, whereas they scored higher in VASI and SSQ. All of the four tests indicated the superior ability of auditory spatial processing in musicians compared to that of non-musicians. Additional to MANOVA, a confusion matrix was done, which is used to analyze the spatial judgmental errors. For example, in this picture, you can see that the 0 degree was confused with left 45, whereas the right 135 was confused to left 135. This is the table which indicates the confusion matrix on different angles for non-musicians, which is represented in gray panels, and musicians, which is represented in white panels. The mean and standard deviation is also mentioned here, and the diagonal bold represents the accurate mean scores for the VAS locations. From this table, we can determine that the confusions were more readily seen in non-musicians compared to that of musicians, and there were more confusions in the left side compared to that of the right side. Moving on to the discussion part, the results of the present study is discussed under the following headings. The lower ITD and ILD thresholds can be attributed to better temporal and intensity resolution abilities, which in turn indicates the larger area activating. Also, the musicians have superior performance on perceptual task, which is a positive outcome on the effects of musical training on spatial acuity. A higher VASI score indicates that can be attributed to superior fine structure processing and memory of speech, both of which indicates higher spatial processing. There were comparison of patterns of spatial errors between the musicians and non-musicians. This can be due to the spatial advantage is more towards the right hemifield compared to that of left hemifield in musicians compared to that of non-musicians. This may be due to the right ear advantage of musicians. A perceptual scale SSQ of spatial hearing suggests perceptual consequences of heightened spatial awareness in musicians. I conclude this study saying that the results of this study provide a new evidence for global advantage on spatial skills for the effects of musical training in auditory domain. Our results set the stage for future studies exploring the benefits of musical training on spatial processing. This effects of musical training on spatial skills can have promising implications on special populations who has spatial deficits like auditory neuropathy spectrum disorder and central auditory processing disorder. I would like to thank the organizers of FRSM 2020, the director of AISH, Dr. M. Pushpavati, the HOD of audiology, all the participants, and all my friends. Thank you. These are my references. Thank you.
So, what is the comparison table? You have compared your result. Have you compared your result? Can you hear me? Hello.
Yes, sir.
So have you compared your result with your state of the art?
Sorry. So 1 second, sir.
Have you compared your result? Compared. Comparison table I'm talking about.
Sir, I cannot hear you, sir.
Have you compared your result? Compared.
Sir, compared with.
Bhumika,
Yes, sir.
have you used, you have used some methods there. Have you compared that the results obtained with your methods with any other method which is reported earlier? Or your result analysis is based on that, that musical and musician and non-musician, in terms of that they are only, across that only have compared. Whether methodical comparison is there or not based on the methods used?
Yes, sir. Sir, ITD and ILD were used earlier by other authors, whereas the VASI, which is a composite of ITD and ILD, as well as the spectral cues, which is important.
The result part. When you have gone for the result part, no, that accuracy is an improvement for that. Have you compared, included that previous method in your result part table?
Okay. Okay. No problem. So I think we are running late. So you have to finish it as soon as possible. Thank you, Bhumika, for your nice presentation.
Thank you, sir.
And thank you very much. So we are going to the last paper ID 54.
You compared it?
Hans Kim. Paper ID 54. Paper ID 54. Hans Kim.
Yes, can you hear me?
Yes.
Yes.
Please.
Yeah.
Yeah. Please present your.
Yes, I'm trying. Yes.
Okay.
Yeah. Oh, I'm not sure how to share my screen. So.
You go to that presentation. There is a present now button. Can you see the present now button?
Yes. Yeah.
You press that
and then
one.
choose.
Yeah.
Yeah.
I think now.
Yeah.
You open your slide and present now button.
3 options will be there.
Yeah.
Yeah, I'm.
You just select second one, a window.
Yes. Oh, yeah. I found the information.
Have you seen that button present now?
Okay.
Yes. Yeah. I think.
Yes.
Can you see?
Not yet.
Can you see it?
Yeah. Yes.
Yeah.
Yes.
Can you? Yeah. Okay. Thank you. Then I start my presentation. Yeah. Okay.
Thank you.
Okay. Hello, this is Hana Kim, a PhD student, PhD in education, who has conducted research in music creativity and well-being. First of all, I would like to express my gratitude to FRSM for providing me the opportunity to present my paper in this conference. Unlike the majority of other presentations in this conference, my study was based on social scientific research, and I took humanistic approach to discuss the concept of mental health. In this presentation, I will first illustrate my insight to the features of contemporary society in which the concept of mental health have increasingly drawn attention. Thereafter, I will introduce my conceptual research into the term mental health, particularly related to music education, music therapy, and emotion. Following this, I will illuminate the process and the results of my federal inclusive Scottish preschools conducted with the aim of strengthening mental health with interventions, educational interventions, and therapeutic interventions. Yes. So, how have you been doing recently in this pandemic situation? When we listen to the news, read newspapers, and approach research documents and articles that discuss COVID-19, the concept of mental health appears quite often. As being emphasized in the press, mental health has been arisen as a term that draws attention and being studied in contemporary society. Contemporary society represents a wave of development in human affairs. Resting upon rapid technological innovation, it has created great opportunities for feeling and expressing creativity. However, it became threats to human well-being resulting from the dislocating social and emotional impact of new styles of living. Moreover, the most eminent feature is that not only adults, but also increased number of young children and pupils are suffering from mental health. As a result, mental health has arisen as an important theme in current era, chiefly as assets and attitudes required for humans to respond, cope, and prosper. So what does the mental health actually mean? According to World Health Organization, the term mental health refers to a state of well-being in which individuals realize their own abilities to cope with their normal stresses of life and work productively to make contributions to their communities. Addressing the features of and phenomena of current society, the role of schools for strengthening mental health for pupils not only in special schools but also in mainstream schools has increasingly emphasized. The concept of mental health is especially meaningful to be investigated with music education at this time, since human beings have had an enduring relationship with sound and music in almost all cultures on record, even and especially those moving through great change. So the benefits of music on mental health have been recognized in ancient Greeks, particularly in relation to emotions that shape the landscape of our mental and social lives. In line with the family viewpoints that admit and intuit a basic relationship between music, emotion, and humanity, this tradition has always appreciated the potential of music to enhance health and well-being. Eminently, it has been argued that music influences people's body and the emotional life of listeners and makers. Furthermore, emotions are not only just the fuel that powers the psychological mechanism of the reasoning creature, but also parts of our cognitive and evaluative reasoning selves too. Since the period in which monism appeared in Bobb's logic of 1728, the dualism of Descartes' has been challenged with also David Hume emphasizing the embeddedness of human persons in which emotions are rooted and thereby strengthening the fundamental alignment belief that human body and mind constitute one unitary entity. Within this integrated understanding of this nature, human beings create and react to artwork through their mind and body, experiencing extended the extra musical effects that also enhance their health and well-being. The arguments were based on the presupposition that music is created by the expression of emotion and reveals emotion in different degrees and forms, and music affects emotion in terms of arousal and stimulation. So the principal aim of this empirical research of my research was to investigate how schools can address the issues of mental health and consider the potential of music therapeutic interventions to be added in inclusive mainstream education to expand the effects of music on mental health for everyone. Particularly, this research focused on Scottish music education. Scotland's education curriculum document named Curriculum for Excellence was designed in large measure to address the same growing emphasis on health and well-being. First, Curriculum for Excellence makes considerable claims for well-being, emphasizing child-centeredness and autonomy, proposing a process-based curriculum supporting an experience of well-being through interdisciplinary working. Secondly, Curriculum for Excellence consists of the three main strands of literacy, numeracy, and health and well-being, and aims for an inclusive vision of education that places the commitment to well-being at the center of its priorities. Furthermore, Scottish education is especially attractive as a test bed for this work because it appears to be achieving this with a curriculum that is experimental, child-centered, and teacher-centered, and that allows for learners and teachers to have a great deal of autonomy and creativity. For my research, I took two approaches, the strategies of The first part of the research was allocated to investigating and critically assessing the overall environment and atmosphere of the schools and the activities implemented in schools with the intention of enhancing mental health. For this, I chose the ethnography, which with the intention to be fully embedded in the fields and to try to proactively enhance the health and well-being from children. For the observation, I took this kind of formula. Because of the time, I won't repeat this, but I wanted to find out the learning intention, the topics and contents, the order of teaching and activities, and the strategies, and then find out how pupils interact with each other and interact with teachers, and how they participate in their work. Thereafter, I had some interviews with famous experts in this field to conduct the research to find out what their opinions are regarding the issues of mental health in their practice as well. So the question teams included what they perceive as the benefits of music and music education, and what kind of activities they do to enhance the mental health for pupils. To strengthen the some practical reflections, I worked in Catholic schools which the well-being was particularly being emphasized, and the school which had diverse backgrounds, including various children from diverse backgrounds and ethnicity. The result of this research showed that mental health was taking an outstanding place in school philosophy, policy, and curriculum in Scottish schools. First of all, the interviews believed in the power and the benefits of music in terms of enhancing mental health. They believed how music could be the medium for experiencing some feelings, and how it could change the inner minds and result in a consolidation of emotional capacity and also strengthening motivation and confidence. Some emphasize that music can make us being away from our daily routines and feel really relieved and feel like a dreamy world, which will enhance their mental. And then they took some programs and activities to cultivate their emotional resilience as well to prosper in this modern society. There were some common activities that participants took, like singing songs, mediation, circle time, taiko, which is hitting instruments, and some community work as well. Yes, so as seen in above data, it was possible that several themes and eminent features as the outcome of research in this research was showing that schools were really doing well to improve pupils' mental health. First, musical inspirations and activities were made across diverse subjects in the form of blended learning, addressing the philosophy and methods of curriculum for excellence in Scotland. Placing music in different prisms enabled an increasing number of pupils to experience the power of music for all despite their musical knowledge. This phenomenon can be interpreted with the concept of Gardner's multiple intelligences, as connecting music with different subjects could stimulate each pupil's different strengths, set and guide journeys to be positively affected by music. Second, it could be observed that the chosen schools were providing more expertise in music education to increase the benefits of music on mental health. In all schools, a block of timetables and special events were allocated to invite musicians or music students and secondary school students to provide special programs and lessons for improving mental health. Furthermore, in one of the inclusive schools for the hearing impaired pupils, assigning teachers were employed to support those pupils to learn and experience and as other able pupils. In this way, the theme mental health was being addressed not only for pupils, but all for the experts as well, as they could develop leadership and realize the value of knowledge published. Finally, all these types of activities and the environment were enhancing confidence and self-esteem for pupils by providing them the opportunities to be active learners and to cooperate with others. Considering the philosophy of Scottish education and the disadvantaged environments where a large portion of pupils continue to live, music education was particularly in the context of Scottish distinctive confessional sector, assuming a significant role in coordination with religious education as well. Furthermore, devising extracurricular activities such as a school choir, allocating special sessions to get all pupils in the school and be involved in special music lessons, events to let pupils be the performers were affecting pupils' mental health in positive ways as well. As reviewed, The objective of strengthening well-being is being relatively well addressed in Scottish primary schools thanks to the philosophy and guidelines set out in the Curriculum for Excellence and in the curriculums generally encompassing operation of the benefits of music. Scottish schools were providing good models for addressing issues of mental health for all, encompassing a wide range of generations and people from diverse backgrounds. It could be observed that Scottish education system and Curriculum for Excellence currently possess the potential to align mental health enormously effectively, chiefly by nurturing pupils who can respond creatively to our fast-changing world and while fortifying their humanity and resilience. Disseminating the positive effects of music across the disciplines and co-working with professional and neighborhood communities, including school institutions, agencies of private and social enterprise sectors that would expand people's thoughts, minds, and horizons and actual experiences of music should be continued. A number of researchers have stated that music is a non-discriminatory way of engaging people. The present research echoes these dispositions, ensuring that carefully crafted music sessions can afford children opportunities to strengthen their mental health and well-being through the cultivation of empathy, self-expression, and imagination in natural and empowering ways. In line with the aims of cultivating whole persons in the central stages of the compulsory education, music education should continue to harbor rich possibilities for realizing and expressing the core values of progressive education today, promoting mental health as an essential aspect of the flourishing, examined, and lived life. Yes, thank you for listening to my presentation. Thank you.
Thank you, Kim, for your nice presentation, and especially on the mental health, which is very much needed at this point of time. And
thank you.
Hope you will gather more data and will be enriched with your experience and with your benefits for the society. So any questions from the audience? So you're from Scotland? You're talking about Scottish music? Okay. So any question from the audience?
So many concerts are there now, that's the problem. So many are there now.
If not, thank you. Thank you, Kim, for your nice presentation. Now, I think we have covered, yes, total 8 presentation for last 2 hours, 30 minutes almost. And we have really enjoyed, actually I have also enjoyed the sessions. We have learned also various techniques and methodologies we use worldwide for the various speech processing and music. And I must thank to Dr. Anupam Bishop for organizing such a nice panel for FRSM.
Sir, paper 30 presenter is present, so if you allow.
Okay, okay, fine. February 30.
Akash, whether your presentation is not visible.
Hello. Hello. Am I audible?
Yes.
Yes. So first of all, on behalf of the authors, I am not the author, one of the authors. The author of this paper is Dipankar Dash and Rubel Dash. So for some technical glitch, they couldn't present it, and on behalf of them, I am presenting this paper. So I will just give you the abstract of this paper. This paper is on human to robotic voice conversion by employing wave patterns based on gender and emotions. So there are mutual conversions from one voice into another is one of the promising research fields in speech processing communities while working with human voice. Influenced by the rapid interest in this area in recent days, we have developed a system to identify gender and emotions. Example: sad, happy, angry, neutral, and fear from human voice. So a separate repository containing wave patterns of all possible phonemes of male and female voice in different emotions has been developed by employing this system. So similarly, they have prepared another system to convert human voice into equivalent phonemes. On the other hand, like human voice web repository, an additional repository containing web patterns of robotic voice was also been developed there. So finally, those phonemes of human voice are converted into their corresponding phonemes of equivalent robotic voice based on the matched web patterns available in this mapped repository. That's how they have implemented this. They implemented this system. So that's all. I'm really sorry for the technical glitch that happened. So thank you.
Okay. Thank you. Thank you very much. So we are now at the end. I think we have finished all the things, and I think this is not the finish, and we are just starting. This is starting of this collaboration, and hope we'll all be connected and we'll do a lot of work in future together. And we have got a lot of critical comments from the audience, especially the professor from NIT Silchar, and he has given good suggestions to all the audience. So I believe you all are getting benefit out of it. Thank you very much.
So this was the end of the last night's session. We are thankful to our session chair, Professor De and Professor Sinha, for valuable observation and suggestion. It will help us in future direction of research. Now we are moved to the validity session. Over to Malaya Datta madam.
Thank you, sir. Thank you, everyone, for being with us. We'll start our validator session shortly. Thank you.
Sir, is the valedictory session is over, sir? Hello?
No, not yet.
Okay.
Namaskar and good evening. Honorable Director of National Institute of Technology, Silchar, Professor Sibaji Bandyopadhyay, Professor K. Kirti Hirode, Emeritus Professor, University of Tokyo, Professor Isel from Poland, Professor Debasis De, Maulana Abul Kalam Azad, University of Technology, West Bengal, Dean Academics, Professor A.K. Baragnia of NIT Silchar, Professor Nidal Sinha, Professor from NIT Silchar, Professor K.L. Vaishnav, Dean Alumni Affairs, Professor from NIT Silchar, Head, Department of Computer Science and Engineering, Dr. Samir Kumar Bargohain, all the deans, heads of various departments, faculty members, authors, and their participants from India and abroad. On behalf of the organizing committee, I, Dr. Malaya Dattavara, delighted to offer a gracious welcome to all of you to the valedictory function of FRSM 2020, organized by the Department of Computer Science and Engineering, NIT Silchar Assam, and Sir C.V. Raman Center for Physics and Music, Jadavpur University, Kolkata. Now, I would like to request Dr. Samir Kumar Bargohain, Head Department of Computer Science and Engineering, to address the gathering.
Thank you, madam. Am I audible?
Yes, sir.
Honorable Director, sir.
May I request you, sir? Actually, sir.
Yes. Hello. Am I audible?
I think so. He
Yes,
has
sir.
technical issue. I'm
Yes, we
receiving
can.
a message from him. He has some technical issue. Now, may I request our director, sir, kindly address the gathering. Sir, please.
Yeah, Malaya, I think I was able to hear Sumit, but maybe, so are you able to listen to me also?
Yes,
Yes, sir. Yes, sir.
Okay, fine. So the 25th International Symposium on Frontiers of Research in Speech and Music, FRSM 2020. So that has come to an end. And I was present in the inauguration program. So many of my old friends from abroad, they were present there. So listening to their keynote talks that set the main tune for this symposium. And as I see that in India, the people who are working in the area of speech and music, that number is not too much high. But lot of work needs to be done in these areas, and lot of collaborations between speech people who are working, say, in the electronics communication domain or in the CSE area. So they need to work in new appropriate technologies. And the speech area itself is an interdisciplinary area. And I think after these 2 days of deliberations, so a lot of new research ideas have been shared on the platform. And I believe that I do expect that my colleagues at NIT Silchar, they have been able to establish good relationship with the experts across the globe, and so that new research and development activities in the area of speech and music that comes into effect. I do expect that the program has been a grand success. So I'll have to leave for because I have a meeting now. But before that, I think what is say the customary from the organizers of the program is to find out to place before us say about how many participants were there and how many papers were presented and so on. So before going further, I will request Malaya to present the picture that is regarding that the number of presenters, how many were present, and how many total number of participants and so on, so that sometimes we judge the success of an activity by the level of the participation and by the number of participants also. Okay, thank you.
Thank you so much, sir, for your inspired word. Thank you. Now, I would like to invite one of the participants to provide us the feedback. May I request Vishnu to kindly provide us the feedback?
Very good evening, ma'am.
Good evening.
Thank you, ma'am.
So first of all, I would like to thank all the organizers, and I would like to congratulate all the organizers. So because it is a successful 25th edition of FRSM, Frontiers of Research in Speech and Music. So I'm very happy to participate, present my paper in this conference. So we have some international speech collaborations like Interspeech and ICASP, but in India we have one conference that to 25th FRSM. So we should proud of it, and I'm very happy. And first of all, I'd like to talk about the conference. So unlike other conferences, so this conference stick to the deadlines. So whatever the deadline that has given, they are very strict to that. So suppose deadline is 7th means 7th, no extension for that. And that I'm very happy that the conference has been conducted in a proper way. So and I'm very happy that I have met many of the speech researchers in this conference. Thank you, ma'am. Thank you for organizing such kind of conferences. It's a grand event. Thank you.
Thank you so much. Now I would request another participant, Serge Brazier, to provide us feedback.
Hi everyone. Can you hear me well?
Yes.
Yeah. I also would like to thank the organizers for the work that has been done during the last 2 days. Actually, I was hearing about this conference some month ago, and it was a pleasure to participate at this conference and to, of course, from a European point of view, I don't have the same music culture in terms of musical content, style of music, tempo variations, and so on. Of course, my work focuses on more the speech aspect. I mean, the theme is opera, but I was also liking how some participants were tackling the way of detecting phonemes in the different languages in India. And of course, I think I will have a nice inspiration of those works for my future work personally. So thanks for those 2 days. There was a lot of interesting talks from the students and doctors, and I would like again to thank for the organization. Thanks.
Thank you so much. Now I would like to invite Subhana Saturji to provide us feedback.
Good evening, madam.
Good evening.
It is my pleasure to participate and speak few words about FRSM 2020. Many good lectures, ideas, discussion we came across will be helpful in future. Especially we can relate different languages, then different Indian languages, Vedas, Shruti, music, then different instrumental sounds, ragas, sargam, then speech therapy, speech application in healthcare, wonderful, just speechless. I must thank the organizer for recording all the sessions and shared in YouTube. Who have missed some session can watch later. I will share with my students and friends. So thanks for everything.
Thank you so much. May I request Hannah Kim to kindly provide us the feedback.
Yes, can you hear me?
Yes, madam. Kindly proceed. Yes,
thank you very much for the opportunity to participate in this conference, and I could learn a lot, and especially since the topic was quite broad and we could approach the theme in various aspects, and especially I think my presentation was a little bit out of the topic, but I could still join the conference due to the diverse subjects. So I really enjoyed it, and especially when I listened to the presentations more focused in scientific areas, I could learn more how to incorporate those to my research and how to make up my studies for the future studies. And it was really interesting to listen to all the presentations in diverse fields. So thank you very much.
Thank you so much, madam. Thank you. Now, may I request Professor Debashish De from Maulana Abul Kalam Azad University of Technology, West Bengal, to speak a few words. Sir, kindly.
Thank you, madam, and good evening to everybody. And it's my pleasure to be here in FRSM 2020. I was also part of this FRSM earlier version, and this India is a country where there's a large cultural heritage we have, especially the Indian classical music. The origin of classical music is in various parts of India, especially in Madhya Pradesh, and where the famous Tansheng is there. And actually, the music is originated. The class has been originated. The computational music is a part of our system, and system in the sense, if you see the present engineering curriculum, Indian classical music, rather Indian music, has been incorporated. I'm also happy to be a part of the syllabus committee of this, and I'm really excited that that classical music is a part of our BTech curriculum. So nowadays, with the new education policy, now everyone can jump to the interdisciplinary field. For example, the computer science people, or electronics people, or electrical people, or mathematics people, even they can go for music as a subject. So earlier it was not we cannot think of it. So this is the area of research which is interdisciplinary in nature. So I believe that this conference gives the platform of the people of similar nature, of those who like the speech and music together, and I believe that already the platform has been set where we have collaborated, and the more collaboration will come out. And I must congratulate all the team of FRSM, especially Dr. Arindam Biswas. They've done an excellent job for even in this pandemic season that they organized, and they got so many quality papers which has been presented. And for last 3 hours I'm present here, we have got a lot of constructive criticism from the experts, and that will increase the quality of the paper. So this is the new journey, and not only we'll concentrate on the paper presentation. I think this is the time to develop certain softwares which will teach us music. That during this pandemic we cannot go outside home, so we cannot even go to the music teachers. So if we can develop certain software or hardware which can help us in learning at home, so that will be a great thing. So this kind of teaching pedagogy can be evolved. I hope that FRSM will show us the path, and will come up with those solutions in terms of hardware and software. And I also wish best of the luck for future FRSM. Okay, thank you very much.
Thank you so much for kind words, sir. Thank you. Now, may I request Professor Eliza from Polish Japanese Academy of Information Technology, Poland, to speak a few words.
Thank you very much. It was my pleasure to attend this conference. Thank you for inviting me. It's a very nice surprise for me that it was so successful. All speakers presenting very clearly and sharing their ideas, and also a very good organization. So I would like to thank all the organizers for a very good job, and wish you good luck for the future with the next editions of the conferences. Best greetings from Poland. Thank you.
Thank you so much, madam. Thank you. Now, may I request Professor Misel from Poland to speak a few words. Professor Misel, please. Professor, may I audible?
Yes, I am now. Sorry.
Yes. Yes, sir.
Okay, it was really an interesting field, community for me to speak to, and I'm glad that that you liked my talk, and it fitted into this conference. It was really nicely organized from my point of view, even though and the only downside was that I had to wake up a few hours earlier than usually, but well, you can't do anything about the time zones and these differences. Of course, if not the virus, we would meet in the same time zone. And yeah, it was interesting for me to see that basically what I hear from the team that is working on Polish speech recognition here at our research center, and all the colleagues that were presented here, you are basically focusing on the same kind of method. So no matter what language, the methods on the IT side are pretty the same. So congratulations for this conference, and thank you for inviting me to speak to you. Thank you.
Thank you so much, sir. Thank you. So now may I request Professor Emily Wenikes to kindly speak a few words. Professor Emily, may I audible to you, sir?
Yeah.
Yes, may I request you to kindly speak a few words, sir?
Yes, I will. Am I visible? Not yet, I think. How is this? Am I visible, audible?
Yes, sir.
Yes,
You
sir.
are visible as well as audible.
I cannot see that myself. I joined all the compliments and the conclusions of the previous speakers, and although I had to miss the second day of this conference completely, unfortunately, due to my obligations here at Utrecht University, but I can say that my excuse to be not present today was a good one, because we had to award a PhD to one of my students who graduated on a very appropriate dissertation, meaning a study into the music as means to support the processing of song language. So it also comes together, boils down at the same time, unfortunately, because we had to postpone that. But what I can say based on the first day, that I really learned a lot. But it also made clear that we need to learn more and that we have to do more research, but that we also need to learn more from each other. And then I mean this sort of in a cultural sense, that we mean learn more from each other's cultures, more from each other's approaches and attitudes, because although I am a musicologist and I know a little bit about Indian musical culture and ragas, etc., some information were really far off for me, I have to admit. So it was really complicated to get into the matter. And I think, for instance, in my screen is still Charles Barnier. It was also the other way around. When he talked about Western culture and music, it sometimes was maybe a little bit complicated for the Indian participants to really have this cross-cultural influence and learning from each other. So maybe in a future conference, we could also address that more cross-cultural learning from each other in this topic in speech and music. But I was really impressed by the smoothness, how the way this conference was organized already in the beginning, and how it was structured. And I think that needs a very big compliment. In my case, my collaboration was directly by Dr. Anuam Biswas. I was very happy with this collaboration, but of course it's a whole team and it's a very hospitable team. So thank you, Dr. Borsch, and thank you, Dr. Padgiri, etc., for having me here and organizing this beautiful conference. And I hope to see you again in the next future. Thank you.
Thank you, Professor. Thank you. We're looking forward to hear from you. Thank you, Professor. Now, I would like to request Professor A.K. Barhuya, Dean Academics of NIT Silchar, to speak a few words. Sir, please.
Yeah. Thank you, Dr. Malaya Datta Barua.
Thank you, sir.
Very good evening to all. Respected Director Professor Shivaji Bandyopadhyay, dignitaries present in this program, and my dear participants. So first of all, I congratulate the organizing committee and the coordinators of the 25th International Symposium on the Frontiers of Research in Speech and Music. So in this last 5 days, I am sure that the keynote lecture from the experts, for the presentation and for discussion, our participants have got a good input in the field of research in speech and music. And in India, there's a very good scope for doing more research in this field, as the languages, the music, culture in different parts of the India are different, and varieties of language, music are there. So there is a very good scope for doing a lot of research in this field. And I hope this, in these 5 days, through this interaction, there will be a good collaborative projects with the international level, with the help of other experts from other countries. And I am sure that in future, this collaborative, this outcome of this symposium will be some more collaborative projects. And with these few words, I again thank you, the organizing committee. Thank you, Dr. Malaya.
Thank you so much, sir, for your inspiring word. Thank you so much, sir. Thank you. Now, may I request Professor NIT Silchar, sir, to kindly speak a few words.
Good evening.
Sir. Yes, sir.
I don't know. I'm sorry that I could not join my session from the beginning because of my engagement for some collateral academic assignments. So, first thing is what music is my passion, and that brain and related that analysis, like brain waves or any other sort of analysis, that is my dream job, or not dream, or maybe that it is in my heart. So I'm very much first of all, I really congratulate that organizers to make this international conference, that is that, as I said about that day, which is very close to my that heart, that area. And I could not, I really feel bad because I could not be associated with that for 2 days, that one. But for my session, last session, I was associated, and I came to know about a lot more things there. And some of course, some enlightening concepts were presented. And it is really that learning experience to go in the different directions for that, and hope that that will across that disciplines and across that regions, across the cultures, and this will come out for that, expand for that areas there. And hope that with that I once again congratulate and for that organizers for doing the commendable job. Thank you very much.
Thank you so much, sir. Thank you. Now, may I request one of the participants, Sambhavi, to provide us the feedback.
Thank you so much, ma'am.
Good
evening to all. We have come to an end of the 25th International Symposium on Frontiers of Research in Speech and Music 2020. Really, I'm speechless for the amazing experience and wisdom that I have gained through this event. I've attended many workshops and conferences, but I would wish to tell all the organizers of this event that this is the first of its kind of symposium where everything was so perfect and of rich value content: the event management, publicity, communication, public relations, the paper selection process, the rich selection of keynote speakers, the encouraging and very enthusiastic session chairs, the invitee speech, etc., was of international standard and quality. There are there are very few dedicated conferences and workshops on music in India. I feel that I'm really very fortunate that I could present my work in this event. I wish to mention here, especially that my session chair, Professor Sanghamitra Mohanty, had summarized every paper presented in technical session 1 that was of amazing quality and command over knowledge. I'm thankful to Dr. Partha for beautifully coordinating this session. At last, it is really an emotional see off from you all. You have been here as a family for past 2 days. With one promise, I take your leave that I shall wait for the announcement of 26th FRSM 2021. Thank you all, and my very best wishes to the organizers of FRSM 2020. After attending this symposium, I would suggest to change the name of National Institute of Technology to International Institute of Technology Silchar. Thank you all from bottom of my heart.
Thank you so much, madam. Thank you so much. Now, I would like to request Head of the Department, Computer Science and Engineering for NIT Silchar, Dr. Samir Kumar Bargohai, to address the gathering. Sir, kindly.
Thank you, madam. Am I audible now?
Yes, sir. Now you are audible, sir.
Okay.
Sorry, sir. That time actually I was not getting you. That's why, sir. Sorry, sir.
Yeah. Due to technical glitch, I could not start with the beginning. So,
yes.
Honorable Director, sir, Professor Sivaji Bandyopadhyay, Dean Academics, Professor A.K. Borgunia, Professor Nidul Sinha, distinguished speakers, experts, participants from India and abroad, colleagues, students, ladies and gentlemen. A very good evening and a warm welcome to all of you in the valedictory session of FRSM 2020. I consider it is a privilege to deliver the valedictory address at this important and timely 25th International Symposium on Frontiers of Research in Speech and Music 2020. This is for the first time FRSM is organized in northeastern region of India at NIT Silchar, Assam. The basic objective of the symposium was to promote research interest in speech and music among the researchers, where the symposium has provided a good platform for the people from different backgrounds like physics, mathematics, musicology, speech, linguistics, electronics, and computer science. We have been fortunate to have some of the eminent persons from academia and allied areas in the area of speech, music, and signal processing. I am sure that the participants must have been benefited by attending this symposium and hope will open the door of future collaboration. The Department of Computer Science and Engineering, NIT Silchar, has been at the forefront of organizing international conferences like ICA, CNI in the year 2018, BGML in 2019, and very recently we have concluded MIND 2020. Also, international workshops, and the latest being the International Symposium under the able support and guidance of directors. The department has greatly been benefited by having deliberations with renowned academicians and experts in different domains and have been able to draw the limelight both at the national and international level. I must compliment the organization of this symposium for their collective effort they have put in, for the kind of subjects they have tried to address, and for excellent organization of the symposium. I wish they continue to excel in future as well, bring more laurels to the department and institute as a whole. Ladies and gentlemen, I once again welcome you to this valedictory function of the 25th International Symposium on Frontiers of Research in Speech and Music 2020. With this, I would like to conclude my speech. Thank you. Over to Madam.
Thank you so much, sir. Thank you. Now, I would like to invite Dr. Ripon Padgiri, organizing chair of FRSM 2020, to present a vote of thanks. Ripon, sir, please.
Am I audible?
Yes, sir, you are audible, sir.
Honorable Director, sir, Honorable keynote speakers, respected session chairs, dignitaries, authors, ladies and gentlemen. It's my privilege to present a vote of thanks on this occasion. I, on behalf of FRSM 2020 and on my own behalf, would like to extend A very hearty vote of thanks to the dignitaries, keynote speakers, session chairs, authors for your kind presence today. I would like to express our sincere gratitude to all the keynote speakers, particularly Beyond Solar, Professor Sanghamitra Mohanty, Professor Michelle Kosidowski, and Professor Kekeshi Hiroshi for their motivational talk and sharing their valuable knowledge. Thank you very much. I would like to thank all reviewers and the authors for their time and efforts. I would like to thank Dr. Anupam Vishwas for his constant and tireless effort to make this conference a grand success. Also, I'd like to express my gratitude to organizing committee members for their support and encouragement, particularly Dr. Samir Kumar Borgohai, Dr. Malaya Datta Bora, Dr. Chamusri Paul, Dr. Naresh Babu Mupalani, Dr. Partha Pakri, Dr. Pinky Roy, Dr. Saha, Dr. Lekrakpan Dalendra Singh, Vishwanath De, Dr. Shamapada Mukherjee, and all other faculties of the Department of Computer Science and Engineering, National Institute of Technology, Silchar, and Jadavpur University.
Thank you, sir. The end of the story is the new beginning of many others. Let us have a hope to organize similar kind of events in newer future. So thank you once again. Thank you all. Namaskar. Thank you.
Thank you.
Thank you. Bye, sir. Bye. Thank you. Namaste, sir.
Thank you, madam.
Thank you.
Thank you.
Thank you, sir.
Thank you all.
Thank you.
Thank you all.
Thank you all.
Thank you.
Thank you. Thank you, sir. Thank you. Bye.
Bye.
Thank you, everyone. Bye. Thank you. Namaste.